Hello, and welcome to the video of the second edition of the workshop on machine learning and data assimilation for dynamical systems. My name is Rossella Arcucci. I'm one of the organizers of the workshop. The workshop is part of the International Conference on Computational Science 2020. The workshop tries to put together contributions from the fields of machine learning, data assimilation, and dynamical systems. In particular, we focus on the opportunity to use machine learning to assist or replace traditional data assimilation approaches, machine learning to support dynamical systems, data assimilation to improve accuracy of machine learning and or dynamical systems, and finally, the merging of data assimilation and machine learning for dynamical systems. The workshop is an event organized by the Data Learning Working Group, which is part of the Data Science Institute at Imperial College London. This year, we received several contributions. Few of the speakers agreed to record the presentation to be part of this video. So I really want to thank you, all of them. I know that this has been a really difficult moment, especially for some of the scientists that have been involved in the research topics for COVID-19. So I know that also the recording of this video has been for some of them like an extra effort. So thank you very much to all of them and enjoy the video.
Welcome to this workshop of machine learning data simulation for dynamic systems. I'm really glad that this workshop is still carry on, even for the COVID-19 pandemic. I think for this pandemic, this research is actually even more important, and we should pursue on. And in the last 6 months, and DSI have been working very actively in this field. And we actually use the machine learning and data simulations for pandemic trend prediction, for epidemic research. And as we all understand, right, and our systems is a dynamic systems, and the epidemiology research is actually studying in this dynamic systems of the disease transmission. So we have been working quite heavily in this field. And there's a couple of research projects and along this line. One is to do with the trend predictions of epidemics, and based on the SEIR models. And this is, again, a dynamic system models talking about the disease transmission. And then with really the Bayesian methods, machine learning combined with data assimilation to do the parametric tuning and to dynamically adjust the systems to fit the fit the observation and make a right prediction. Recently, we even put more efforts in this area of data simulation and also machine learning for estimating the instantaneous reproduction numbers. Use this one as a tool to evaluate the efficacy of intervention strategy. And this is, again, a typical application where the data simulation will be used to infer, right, the system status. In this case is a reproduction number through the observation. In our case, it confirmed the case. So in general, right, our epidemic system is a dynamic systems, and we make observations based on the reported death numbers or reported confirmed cases. All this observation. What we do is to infer the state, which is the reproduction rate, and infer the status about, for example, how disease transmit, what is the generation time, what is the onset time, all these kind of system variables. So we did very well on this work. So I hope right, our research on machine learning and data assimilation and its combination can provide a powerful mechanism for us to further understanding the disease transmission, understand epidemiology phenomena, and then we can work well to predicting the pandemic situation, particularly to evaluate the effectiveness of different intervention policies and measures. So this is a very good research. I wish the workshop doing well, and I hope this research can actually progress well and more collaboration can be made. Thank you.
First, I would like to thank Rossella Arcucci for organizing this online edition of the workshops on machine learning, data assimilation, and dynamical systems. I believe that producing such a recording of the workshop's contributions is actually a very nice idea, and I would like to thank Diana O'Malley for helping to set this up. So the results that I will present is a joint work with Julien Brajard, Alberto Carassi, and Laurent Bertineau, and it has been supported by the REDA machine learning project. So this study is truly at crossroads between data assimilation, machine learning, and dynamical systems. And the goal of this study is to estimate the dynamics of a chaotic system from partial and noisy observations of this system. And the natural output would be a surrogate models for the true dynamics. The sub-goal for this system is to, for this problem, is to estimate and minimize the errors that are attached to this estimation. And this is something quite original in this work, because we're going to this to achieve this sub-goal, which is something new. There have been many references on this fast-growing subject of trying to reconstruct the dynamics using machine learning techniques, and I give some of them in the bottom of these slides, and you can find these references at the end of my presentation. But there have been many more since the beginning of the year 2020. So many references to check upon. So to achieve our goal, we need to formalize the problem and choose mathematical representations for the dynamics and for the surrogate dynamics meant to represent the true dynamics. So one simple but efficient choice is to use a set of ordinary differential equations to represent the surrogate dynamics through this first order set of equations here, where phi of A is the tendency, which is parameterized by a set of coefficient of NP coefficient in A. We need to integrate this tendency between time tk and time tk plus 1, where we are going to have these get these observations on the true system, on the true dynamics. So we need to be able to build a resolvent, this capital F of A resolvent between tk and tk plus 1 by integrating those tendencies. So we need to make some choices on the numerical integration scheme. We have also to specify mathematically the form of the tendency, so the parameterizations that we choose for phi of A. But very importantly in this work, we actually go beyond, because we will estimate the errors in the estimation process. So that actually the dynamics that we are going to estimate is not an ODE, but it's more generally a stochastic differential equations based still on the deterministic tendency phi of A, but there will be also some stochastic process that represents model error that we make in the estimation of the surrogate model. So this is actually more general than just the set of ordinary differential equations representation. So the first step is to devise the integration scheme to move the system from time tk to time tk plus 1. So this is illustrated by this diagram where we have to build this capital F of A resultant of the surrogate dynamics from the observation vector yk to the observation vector yk plus 1. So we could choose a numerical scheme like the Runge-Kutta method, okay, integrated over some short time step. This is a sub step between tk and tk plus 1. And it, of course, depends on the tendency that we will have to mathematically represent. And then, as needed, we can actually compose those integration schemes several times, like NC time, to really move from tk to time tk plus 1. So this is the Runge-Kutta scheme integrated composed several times if necessary. And now we have to make a choice for phi of A for the tendency. So we have tested many architectures for the choice of phi of A, and in particular two strategies. One is to have a minimal representation with as few parameters as we possibly can for A, and this actually has been very successful, but may not be scalable to high-dimensional problems. And the second strategy is to use a neural network with potentially many more parameters, okay, to parameterize those neural network layers within the neural network. And this has been implemented in TensorFlow 2. Okay, and this is mostly what we are going to use in this study, but both are implemented in our code. Now we have to make some choices based on the symmetry in the system, and we are mainly interested in geophysical systems that usually have local dynamics, meaning that the tendency at some point, some location in space, it only depends on a stencil at some surrounding points. Okay, those are for the tendency. Doesn't mean that you can't build up long-range correlation in the system. This would actually this would be produced by the integration in time. So the system is assumed to be local, but it could also be homogeneous. That is to say, the dynamics could be invariant by translation in space. And this would make us use convolutional layers to represent the neural network. But assuming that the system is not homogeneous but heterogeneous, then we would have to use locally connected convolutional layers to make this dependent in space explicit. But we would still assume locality of the system. So here's this phi of A tendency representation through a neural network. And we are going to use linear activation function. We've tested several activation functions, but here we're using linear activation function. And the nonlinearity is actually coming from an explicit bilinear product that we make from the first convolutional layer here. And so this is the product of the layer producing bilinear terms, but we also use, of course, linear terms that are coming from this first convolutional layer. And we concatenated those contributions, and then through a last layer we end up getting this tendency. So this is the neural network representation of the tendency, which are integrated from the explicit scheme, and in particular here the second order Runge-Kutta scheme. But in the numerical experiment we're going to use actually the fourth order Runge-Kutta scheme instead. And then if need be we can compose those small f of A okay, to build up the full resultant between tk and tk plus 1. So this is our surrogate model representation and its integration. So now we are able to move from tk to tk plus 1. We can actually build a statistical problem, the inverse problems to build the surrogate dynamics. This is the last component that we need to formalize our problem. And we have a Bayesian view, like in Data Assimilation, on this inverse problem, and in particular here on the joint problem of estimating both the dynamics and the state trajectory within the window. So this is the surrogate dynamics, okay, through this A coefficient, and some model error okay, which is encoded here in this Q matrix, and the state trajectory from t0 to time t capital K, which is the beginning of the end of the window. And this is conditioned on the observation on the system. We're going to assume that we know here the observation errors, statistics, this R matrix. Okay, because this is the this is not the crux of our problem, and so we don't necessarily want to estimate those R matrix in this formalization. So the conditional PDF that we are interested in, this one, and to make it explicit, to build it up, we need to use this hierarchical decomposition, Bayesian hierarchical decomposition, which leads to the product of the likelihood of the observations knowing all the other variables in the system, of this prior on the state trajectory within the window knowing the dynamics, and of this hyperprior that we have on the dynamics and the errors attached to these dynamics. Now, assuming Gaussian statistics and a Gaussian assumption that we make on the errors and Markovian dynamics, we can actually make this decomposition explicit and build a cost function, which is minus the log likelihood. And this yields this sum of terms. First, a term that which is the departure from the observation, and a second one which measures the discrepancy between the due to the surrogate dynamics. Okay, it really looks like weak constraint for the var as used in data assimilation. Okay, except here that we not only have to estimate the state trajectory x between t0 and tk, but also the model parameters, the surrogate model parameters, and possibly the error, model error statistics. The very strong point about this formalism is that now we can handle partial and noisy observation. This is something which cannot be easily done with standard machine learning techniques. And actually, machine learning loss function could be recovered, taking a limit where the observation noise is going to 0 and where the system is fully observed. In this case, the data assimilation cost function that we built here as the limit of this least square machine learning cost function. Okay, now we need to solve, to optimize over this cost function, and we need to make some choices because there are many variables, and so we need to choose which variables to optimize on, and also to choose the numerical technique that we're going to use to optimize on the cost function. So first we're going to work on the Bayesian analysis of the joint problem. By joint I mean estimating above the surrogate model parameters and the state trajectory within the window. And here we're going to assume that Q, so the errors, the statistics of model errors are known. And this leads to this cost function. Okay, and we have tested several ways to actually solve this problem in our past papers, and one of it is just a solution can be obtained through a full variational approach, where we optimize on both A and the state trajectory within the window, knowing Q, and this is in the form of a full weak constraint for the var. This is actually successful, but it has limitations when we increase the length of the window. Okay, due to the optimization technique. And the second approach, which doesn't necessarily have this limitation, is based on a coordinate descent, where we do understand that the variables for the parameters in A and the state variables are behaving very differently in the optimization. So we split the optimization in two steps that we iterate. The first one is using a weak constraint for the var. First approach would be to use a weak constraint for the var to solve for the state trajectory within the window, and then optimize on A using another variational problem, and then we would iterate this. And another approach would be to use an ensemble command filter to estimate the state trajectory within the window, and then use again the variational subproblems to solve for A, and then we would again iterate. Okay, so this, but both approach are really based on this on a coordinate descent, and this is formalized by this algorithm that really combines data assimilation machine learning techniques by iterating on them. And we start with an initial conditions for the model parameters, but also for the state trajectory, possibly using interpolation. And the first step is in fixing the surrogate model. We estimate the state trajectory within the window using data assimilation. So it could be using an ensemble command filter or an ensemble command smoother. And the second step is to fix this estimation of the state trajectory and to estimate through machine learning techniques this set of parameters A. And then we would iterate until convergence. Now, another a way to formalize the problems is looking at the Bayesian analysis of the marginal problem. By marginal, I mean focusing only on the estimation of the dynamics and not the state trajectory specifically anymore. In addition, we are going to now assume that Q is not known, so that we, of course, we know that we don't know very well the errors that we make in estimating the dynamics, and so this error will be part of the estimation. And so what we like to focus on is this marginal PDF, okay, on A and Q condition on the observation. And we have no analytical formula in general for this PDF, so we need to use an integral to make it explicit, to link into explicit a conditional PDF. We need to integrate over the state trajectory within the window. This is the integral that we will have to formally solve to actually be able to have an analytic expression for this conditional PDF. And assuming we can get one, we would use this loss function. So, as I said, in practice, this is not possible to have an analytical solution. And but there is one excellent method to actually estimate the maximum a posteriori, so the map of this conditional PDF, of this marginal conditional PDF, this is the expectation maximization algorithm. Okay, and it has been suggested in this scope, in the reconstruction of a dynamic system, quite some time ago, in this reference, using an extended command smoother. It has also been suggested to estimate subgrid stochastic processes in Pulido et al. 2 years ago using an ensemble command smoother. More recently, it has also been suggested, the expectation maximization approach has been also suggested using an ensemble command smoother in Nguyen et al. Last year. But in practice, the numerical application and our approximation that they are proposing is actually a coordinate descent algorithm where model error is not controlled. So this is not really per se an expectation maximization algorithm and would yield different results. So the expectation maximization is, I don't really have time to go into the details, but this is really a way to solve for the maximum a posteriori of this conditional marginal PDF, not knowing and the analytical results for this integral. Okay, and it goes in 2 steps that we iterate. The first step is the expectation step, where we compute the expectation of the log likelihood of the joint log likelihood, and this is something that we can write analytically. Okay, and second steps, once this is obtained, when this expectation is obtained, it's to optimize this expectation and look for a local minimum on the parameters. And once you've done that, you can iterate until convergence on the parameters. It turns out that there are cases, very interesting cases, where you can do everything analytically Okay, but these expectation steps in general is not that easy to carry out, and one way when we don't have analytical results, we can actually use Monte Carlo technique to estimate this expectation. Okay, and this is called the Monte Carlo expectation maximization, and this is something that we can actually do here because we have an ensemble that is the outcome of the ensemble command filter or ensemble command smoother within the window. We can use this ensemble to average upon the ensemble members and have an estimation of this log likelihood within the window. So this is what we're going to use. And first I'm going to describe the full expectation maximization algorithm applied to our problem. And the expectation step is based on the ensemble command smoother that would use the model error, that would take into account model error through a dedicated scheme. And the output would be the a posteriori ensemble that would be generated by the ensemble command smoother. And then using this ensemble, we could actually write down this L function that depends on A and Q, and to compute this expectation over the ensemble. And that would be the cost function that we would have to minimize over A and Q. To do so, we can either implement a joint optimization, that's something that we have tested, or maybe a more, maybe smarter way to do it is to use a coordinate descent over A and then Q, or Q then A, which alternate the minimization on A here. So this is achieved through machine learning techniques. And the estimation of Q, which can actually be carried out analytical using the Gaussian assumptions that we have on model error. Okay, so now there is an exact explicit analytical formula, but using the ensemble that have been calculated in the expectation step. Okay, and now we iterate this coordinate descent to have an estimation of the minimum of this function on both A and Q. The point is that it could be extremely costly because of the storage needed to store this ensemble over the window, the ensemble of trajectory within the window, and because of the computational load where we have to make all those sum over the ensemble and the time steps. So we were able to actually do so on low order model, but this is extremely costly, would be extremely costly on a higher dimensional system. So we've been looking for an approximate way to carry out this scheme. And first step would be in the expectation step would be to use still this ensemble command smoother. Okay, and but the output would be first the mean of the ensemble and not the full ensemble. And Q would be computed online. Q would be computed online, meaning that we would use the ensemble through the analytical formula of Q to estimate Q within the expectation step, not waiting for the maximization step. Okay, so the output of the expectation step is this mean trajectory together with the this updated estimation of the Q matrix. Okay, now in the maximization steps, knowing that we have estimated already Q matrix, we really have to focus on A, on the parameters of the surrogate dynamics, and we optimize using machine learning. Okay, but now we don't have to use the full ensemble, we use this mean of the ensemble. So we don't have to store the full ensemble at all. Okay. And so we have actually seen that in all the numerical tests and models that we've used, it turns out that the full and approximate schemes gives very similar results and very similar performance. That is why most of the results that I will show are carried out with the approximate solution, even though we have also tested many of them with the full solution. So let me go to the numerical experiment, and so we are going using low order model, chaotic models. We are going to build those surrogate dynamics and also use metrics to tell us how good is this surrogate dynamics and how well it represents the true dynamics. So using a forecast skill measure, okay, which is measured by a normalized root mean square error between the reference dynamics, the true dynamics, and the surrogate model dynamics. And those are computed using forecast as a function of forecast lead time and average over many initial conditions. But this is for just forecasting at short on midterms, but we are going also to use Lyapunov spectrum and power spectral density, which are representative of the long-term properties of the surrogate dynamics. And a typical output for reconstruction of the dynamics is that, so using here the Lorenz 96 40 variables model, which is chaotic dynamics, typical toy model in the geosciences. And this is the comparison. This is an off-model diagram where we compare the true dynamics with the surrogate dynamics starting from the same initial conditions, and we see the errors that emerge with time in between the two dynamics here. So this is a typical graphical example, but here we mainly focus now on statistics, on the short-term and long-term properties of the surrogate dynamics when we intend to reconstruct the Lorenz 96 model. And we see here the forecast skill, and we made an ensemble of experiments so that actually you see several curves over there, and the mean is the dashed red line. And the Lyapunov spectra is extremely close to the true spectra of the spectrum of the true dynamics. Okay, I mean down to the negative Lyapunov part of the spectrum. And as expected, the power spectral density is a very good match for all the slow component and intermediate component of the spectra. And of course, there is a discrepancy for high frequencies. But I must say that if we don't account for this stochastic part of the estimation, for the stochastic part of the surrogate model, it turns out that the fit would be better and will be very close to the true solution. But that would not be a reliable estimation. And accounting here for the model error that we make in the estimation, we have something which is much more reliable and really clearly says the limitations of this estimation, okay, on these high frequencies of the power spectral density. And we have also tested the methods on the two-scale Lorenz system, where we observe only the coarse modes of the dynamics, not all those fast modes. So the coarse modes are the x variable, the fast mode, the u variables. And we only estimate the coarse modes. We only observed the coarse modes, only built surrogate dynamics for the coarse modes. And this is again a off-model diagram where we do see differences between the dynamics, with the emergence of errors coming from the fast motions here, and okay, that are moved in the fluids of these two-scale dynamics. And we also computed the statistics, and we see some stronger dispersion with the experiment when changing the seed of the experiment. And we got a Lyapunov spectra which is shifted, and that's because now we don't have an exact correspondence with the true dynamics, and so there is a difference in terms of energy for the surrogate model representation and the true Lyapunov spectra, and this is why there is such a shift between the true two-scale Lorenz model and the estimated ones through the surrogate dynamics. And this is the power spectra, where we have a very good match for high low slow motions and slow scales, and of course a discrepancy at higher frequencies. Now we have studied the dependence on the window length, and you see that it gets better and better as we increase the window length, which is exactly what we would have expected with this Lorenz 96 model, where we can get very close to the true dynamics using the surrogate model. So it keeps increasing with the length of the window and getting more and more observations. But this is not the case for the 2-scale Lorenz model, because there is a saturation. We can't really get to the bottom and the true dynamics. And there is a point beyond which there is no need to assimilate any more observations, because we essentially get all the information that we needed to have some reasonable estimation of the surrogate dynamics. So there is a saturation at some value of k. And this is something that we also see in the magnitude of the observation noise. So for the Lorenz 96, it gets better and better as we decrease the noise. But this saturates when for the 2-scale Lorenz model, as we decrease the noise magnitude, we've got a saturation effect, because the true model cannot be reconstructed beyond some point, and there is still a residual error, and there's no point in getting finer and finer observations on the system. But we do see some improvement in the power spectra as we get finer and finer observations. And to demonstrate the strength actually of this data assimilation approach, we also use partial observations. And we also studied the dependence on the observation density in the system, and we got those consistent results. When we increase the density, we of course get better results. And something very similar for the 2-scale Lorenz model. Okay, so let me conclude for this study. So all the results that I've discussed are actually in these 3 papers that are referenced at the end of this presentation. The main messages that I have is that that we have built a Bayesian data assimilation view on state and model estimation. Then data assimilation can address goals usually assigned to machine learning, okay, but with partial and noisy observations. And that's a very strong strength of this approach. The numerical cost of high-dimensional systems are significantly reduced by the use of locality assumptions, which is fine in geophysical systems, but also homogeneity assumptions, but we can do without it. Now, the core of this work is the use of the expectation maximization technique, okay, with those 2 full or approximate variants, and it has been successfully achieved. Okay, but so far, before this paper, we only had coordinated minimization applied to the reconstructions of the dynamics, and so this is the first time that the expectation maximization technique is really demonstrated on low-order systems. And because of these iterative schemes, both on expectation maximization and this data assimilation machine learning approach, we can actually handle very long training windows, and so a lot of observations if need be. And this has been successfully applied on 1D low-order models, and we've shown the 1-scale and 2-scale Lorenz model, but we also worked on the Lorenz 63 and Kuamato-Shiva-Shinsky models. Okay, in presence of partial observations and significant noise. Now we have answered quite a few questions that we have 2 years ago and the reconstructions of those dynamics using machine learning and data assimilation, but there are still open questions that we haven't really answered or tackled. First one is the use of non-autonomous, reconstructing non-autonomous dynamics, and that's an open, difficult questions. Another one is the use of implicit integration schemes, because here it was focused on Runge-Kutta, which are explicit schemes. And this is meant to be much more difficult to implement. Another one is the use of online learning scheme, because here we assimilate observations that we have given all together within a window, and we will try to estimate on this window the dynamics. But what if we received sequentially those observations? That would require other schemes. And finally, is the scalability of those approaches. Can we use more complex high-dimensional models to apply them on? Okay, thank you very much for your attention. And you can find the references at the end of this presentation, so including our references and also all the references that we used in the course of this study. Thank you very much.
Welcome to the presentation on the recursive updates of wildfire parameters using barrier points and ensemble Kalman filtering. My name is Raymond de Kalfan, one of the co-authors of the paper, and I'll be presenting together with Abhishek Subramanian, sorry about that, who is the lead author on in the paper. And other co-authors are Litan, Daniel Kroll, and Ilka Antitosh. And the last two authors are part of the San Diego Supercomputer Center at UCSD, and both Abhishek and me are part of the Department of Mechanical and Aerospace Engineering at UCSD. Now, just before we get started and look at some of the details of the talk and the presentation and the paper, I wanted to give you a little motivation why we looked at this particular work as part of the Wildfire project that looked specifically at the wildfire modeling, and some of the implementation of this work is done within FireMap. And FireMap is basically a website that allows you, it's kind of the Google Maps, if you will, of fire modeling. And all this work was a joint effort between UCSD, the Department of Mechanical and Aerospace Engineering, and the San Diego Supercomputer Center, but also the Fire Engineering Department at the University of Maryland. So the objectives of this talk was to particularly look at techniques for real-time wildfire perimeter location prediction. And the way we like to do that is to use weather and field data combined with fire models, in particular FarSight, and use data assimilation techniques based typically on Kalman filtering to improve these wildfire perimeter location predictions. On top of this, we also try to improve the aspects of the wire predictions by learning the fire behavior, in particular, learning where fire parameters stop burning, or we call them barrier points. And both two aspects have been incorporated in this presentation, also in this paper, to improve the prediction of the wildfire. Just to give you a little overview of what we're going to present today is I'll give you a quick overview on the wildfire modeling using FarSight, and I'll show you a few slides what we did to extend FarSight to improve the data assimilation aspects. In particular, I'll talk about the introduction of uncertainty in the wildfire perimeter, and also how we identify stationary points, and we call them barrier points, as part of the wildfire assimilation process. Then Abhishek will pick over and talk a little bit more about the data assimilation and illustrate these results on 2016 sand fire that was burning here in California. And we were fortunate enough to get quite some data of the fire, and we actually were able to do some assimilation of this fire. And Abhishek will say a few more results on those. So just a few words on wildfire behavior. I think everybody will understand that this wildfire is a fairly complicated process. It's a complicated feedback interaction between the actual wildfire itself and also the atmosphere that drives the wind, if you will, the temperature and humidity that drives the wildfire, and vice versa. The wildfire can also change the atmospheric conditions. And the relevant parameters for such a wildfire to do some kind of simulation is typically the weather, the weather itself, which involves wind speed, humidity, temperature, but also the topography of the landscape, and then the fuel content on the landscape. You know, how's the landscape covered, and then next to that, of course, there is the initial perimeter where the fire starts. Now, in the research field on wildfire modeling, there are lots of models out there that do very detailed fire modeling. But what we wanted to do in our work is to actually work with relatively simple models that include also a lot of uncertainty on these particular parameters, like weather, topology, fuel, and perimeters. And the simplified models, although they're not perfect, they can run relatively fast. And the idea is that although we're not perfect in simulating the wildfire and not taking all the complicated interactions into account, we hope that any errors that are created by the simplified model can be corrected via a data assimilation procedure. And data assimilation is nothing else, is actually taking then the measurement of where the fire is and correct the model and adjust for it. So next time we can do a better prediction. Again, the reason why we use simplified models and data assimilation is to make sure we can run these simulations in near real time, so they can be used for real-time predictions of where the fire is going to go during an actual wildfire event. So what we do for that simplified model, it's basically Farsight. It's a model that allows you to compute wildfire growth using those same parameters: weather, topography, fuel, and perimeters. And from a bird's eye view, basically what it does is you start out with an initial fire perimeter, which I indicated here with a slightly small little purple 4-point perimeter. And what you do is you use all the topography information, the weather, fuel, and actually do a so-called open loop simulation. And it basically can then predict in, let's say, in this case, an hour further down where the fire is going to go, maybe 2 hours, 3 hours, and 4 hours. Those are these different colors that I indicated here. And it's basically, from a computational procedure, it's an open loop simulation. It's basically a nonlinear dynamical map that maps all the information on parameters, the initial perimeter of the fire, to a new update. And on top of that, Farsight also allows you to use barrier points. That means it basically you can allow to stop the fire. Think about maybe there's a firefighting effort going on that actually removed or extinguished some of the fire or changed some of the fuel content. And that concept of barrier points is very powerful because it allows you to actually change how the fire grows over time. Now, there are some limitations. First of all, the computations that are done, which we indicated by a state, is typically only the fire perimeter, but of course, the actual fire might also have contained some unmeasurable quantities, like fuel moisture might change, might be fuel adjustment factors. These things are hidden inside the model, but typically not directly visible when you do your fire simulations. Typically, there's also no probability or uncertainty characterization. The fire is simulated, and there's no variability with respect to the fire simulation. And furthermore, which is kind of important here, is that it does not use any real-time measurements to maybe adjust or update these fire perimeters as you go through this process of predicting where the fire go. Right. So this is kind of the idea of Farsight. And I like to point out is these simulations of simulations of fires, depending on the size of the fire, can be done within 5-10 minutes. So these models are relatively fast and could be used to do multiple simulations in a short time frame. And you can also parallelize this. So some common observations, we worked on these Farsight models before, is that typically we see on long temporal scales, so long predictions ahead, it may incorrectly predict the wildfire spread due to the kind of coarse nature of both the spatial and temporal data, right? We also see that Farsight uses a high resolution internal state, which is the actual fire perimeter, very detailed. But typically, when you get measurements out in the field, they're a much lower resolution. And we use a different variable here we call yk, or yk plus 1, meaning the next time instant k plus 1, given measurements from the previous time instant k, while the state, again, is typically much higher resolution. And again, you can use barrier points where you say that at some point in time, the fire perimeter at the next time instant, k plus 1, is equal at the previous time instant. Again, it doesn't have to be the whole fire perimeter, but parts of the fire perimeter are the same during this fire spread. Now, what was now our approach in our paper is to actually try to use uncertainty on the observations, because we do get these observations, but they're not perfect. And we like to take these uncertainties into account to make decisions on how to improve the fire prediction. Also, we like to identify barrier or stationary points when we get those observations. And of course, the data assimilation technique. So once you do get these observations with uncertainty and barrier points, can you use that to improve the prediction where the fire is going to go in the next time instant? Now, how does that work? We'll start first a few words on the actual variability, and then I'll say a few words on the stationary points, and then Abhishek will talk about the actual data assimilation. So the first thing we do is we characterize uncertainty by taking any point on the fire perimeter and associate with that point a probability where that point might lie. So imagine this probability could be associated to the measurement accuracy. It could also be associated to the fact that we simply don't know exactly where the fire is, and we can assign a probability where the fire perimeter would be. So we characterize that by, of course, the mean value where the point is, but also, a sigma value, 3 sigma value. Think about the normal distributions in an x direction and in a y direction that possibly could be rotated. So you end up with these rotated ellipsoids characterized by a so-called covariance matrix that takes into account both the uncertainty in the x and the y direction and the possible rotation of that ellipsoid. And we extend that actually out to the full perimeter. So every point on the perimeter, as indicated in the figure here on the right, you see all those little points, and every point has an associated uncertainty around it. And you can imagine if the uncertainty is really small, then you know that it's a very accurate measurement, and our fire simulation should be close to where that measurement is taken. While other points where there's a lot of uncertainty, we allow a little bit more variability or offset, if you will, in a fire simulation. And this is going to be crucial later on when we do our data assimilation. Now, the next thing is the barrier points. And what do we mean by that? Well, here in this picture, what you can see is in this particular case, a fire perimeter, the blue line, was measured, let's say, at a particular time. And maybe 1 or 2 hours later, another fire perimeter was measured, which ended up being the red line. And you'll see that the red line has extended at a certain point, but at other points, it has not been extended. Now, keep in mind that those fire perimeters are not measured always the same way. They might start at the different starting points because they're polygons. And you can see that here we left these polygons open. There's a starting point over here and then goes around and ends up here. And while the other measurement started over here and goes around and ends up somewhere here. So the first thing to do to identify stationary points, i.e. points that have not moved, what we do is we characterize our fire perimeter as a polygon, an ordered polygon of both x, y coordinates, and we represent them by complex numbers, and we apply on these polygons the so-called Fourier transform, and basically representing everything in a complex domain that allows us to do a very simple phase shift that basically moves points around. And the phase shift is just accomplished by a simple multiplication with an exponential function, and I again here is the complex number. And the reason why we do that is because this allows us to reorder the polygons so that we get the best phase shift to make sure that points are lined up correctly. And then in this way, we can then compare two perimeters and decide if certain points are indeed stationary points, i.e. have not moved from one time step to another time step. Now, the learning of the stationary points is then based on a simple comparison of a fire perimeter at, let's say, time instant k, and the next time instant, k plus 1, which is then this one is reordered, and make sure that the distance between those points are below a certain boundary. If that's the case, we then quantify that point on the perimeter as a stationary point. And we indicated here, by the way, in this figure, the stationary point by little black squares, and you'll see that later on in other pictures too. This allows us to say that for those points, we don't have to predict where the fire is going to go. We know it's a stationary point, and for that, we do not have to do any assimilation. We know the fire is going to stay at those locations. Now, with these two information, both the uncertainty and the stationary points, we're going to now look at how we're going to actually update the fire perimeter using the data assimilation techniques. And for that, I'm going to switch over to Abhishek, and so he can pick up the discussion from here on out.
Thanks, Raymond. So in this slide, we can see an illustration of what we actually do. So like Raymond mentioned, Farsight is the fire model that we use to determine how the fire perimeter progresses over time based on some data that we already have, like the weather data and the fuel data. So this is the prediction step that we use. And we take in the, once we have the prediction step at a time step k+1 using the previous data points that we have, we take into consideration the observation whenever that becomes available. For instance, if the fire department makes an observation of how the fire has progressed, we take that into consideration, and we also take into the consideration the uncertainty of the observed fire perimeter, and we form a feedback loop, we use the ensemble Kalman filter technique to combine the two, the prediction and the observation, and then give the new updated fire perimeter back into a prediction model, and then so on and so forth. This keeps going on, and we progress the fire perimeter. And ideally speaking, with our observed fire perimeter and the predicted fire perimeter, when we have both of them, we try to minimize the uncertainty using this ensemble Kalman filter step. So going over the individual steps of what actually happens, like we mentioned earlier, in the prediction step, we initialize the distribution. This could come from either an observation or an initialization that we make a best guess, and we generate ensembles. So for the data that we're going to show, which Raymond mentioned, we got from the Sand Fire that happened in 2016, we generated about 100 ensembles, and we use that for our data assimilation purposes. And once we generate, we have an initial distribution of the perimeter, and we also assume a covariance. We also develop a covariance matrix. So using these, we generate 100 ensembles, and each ensemble we ran that through the Farsight model, which was our prediction step. And once we ran each ensemble, we got 100 ensembles as a predicted step. And for the new step, we were able to determine the predicted sample mean and the sample covariance using the new data points that we obtained. And having the predicted fire perimeter at a given time step, if we ever get an observation step, we take into consideration the observation and the uncertainty on those observations, and then try to combine the two. So when you get the observation, we also get that in terms of a fire perimeter, and we also get a covariance for that. And using the predicted mean sample and predicted covariance, and the observed fire perimeter, which we assume to be the mean, and the observation covariance, we develop a cross covariance matrix, and we use those two to determine what the Kalman gain would be. And the Kalman gain is formulated in such a way that it takes the uncertainty of the predicted step and the uncertainty of the observed samples and tries to minimize the two. And once we get the Kalman gain, we use the formula to update the individual fire perimeter and the covariance using this formula, which you can get a lot more details on this in the paper that we have written up. So now we get the new adjusted sample mean and sample covariance by taking the predicted step and the observed fire perimeter as well. So from now on, I'll talk about the actual results that we got from the Sand Fire data that we obtained. In the year 2016, there was a wildfire that broke out in the Angeles National Forest in Los Angeles County. This started at about in the afternoon around 2:10 p.m. in July, which is typically when the fire season starts. And by July 25th, it had reached quite a large extent, almost came into San Diego as well. Although it is unfortunate about the fire, we were able to get good data to develop this algorithm, which we think will help for future fire predictions. So we use the data for modeling and assimilation. We determined what the fire perimeter is at a given time step, and we progress that over several time steps to determine if we can match both the observed fire perimeter and also the predicted fire perimeter. Now, if you look at this image, the blue perimeter was the first piece of data that we obtained, so we assigned that as time step 0. And the red perimeter is the data that was observed at 4 hours, at a point 4 hours later. So you can see that we for the blue perimeter we assigned a uncertainty based on the density of the observations that we received, and we also determined the uncertainty of the red observation based on the density of the observations that we received. But you can see between the blue perimeter and the red perimeter, there is a portion of the perimeter that did not move, and these are what we assign to be barrier points that are which are indicated through black squares. So using and on the right side, we also got an observation which was obtained 16 hours after the initial fire perimeter was obtained, which is indicated in green line. So red line was at 4 hours and green line was at 16 hours. And even between the red and green, you can see that some parts of the fire perimeter actually did not move, and we classified these to be barrier points. And we also assigned uncertainty for the fire perimeter that was obtained at 16 hours. So using all the data that we obtained, we are showing one time step of both the prediction using our farsight model and also the observation that we obtained from the fire department. So with the green perimeter showing what was observed, we have our predicted step, which is shown in the blue line. So from time step where we had the red perimeter, we used the data modeling in farsight to progress the fire to 16 hours. So as you can see here, the blue line is what we determined from our farsight modeling, and green line is what we have observed at a point 16 hours. So you can see the uncertainty that we obtained with our farsight model as well, based on the number of ensembles that we determined to run through. And you can see how the combination of a predicted step and the observed step gives a much better fit of the fire model. And that can be very clearly seen in terms of the uncertainty. So the black perimeter that is shown here is a combination of the predicted step and the observed step. So in the black perimeter that you see over here, with the uncertainties in red circles, you can see that the uncertainty of the red circle is smaller compared to both the predicted step and the observed step. And the individual pink dots that you can see in all over the fire perimeter are the individual ensembles, which was used to determine both the mean and the covariance. So the overall goal is to assimilate the data that we have in the prediction and the observation and try to minimize the uncertainty of the fire perimeter itself. So to make this concept, to understand this concept better, we went ahead and created this illustration to show how the error, what the maximum error is, what the mean error is, and what the minimum error is in the data assimilation process of the fire coverage area. So assume that the black perimeter over here is a predicted fire perimeter, and the red perimeter over here is the observed fire perimeter. The best case scenario where the minimum, where we get minimum uncertainty is illustrated here. We take into consideration both the mean and the uncertainty of each individual points. And the worst case scenario of the error would be in this, is illustrated as the image C, where we take into consideration again the uncertainty and the mean. And the mean of the error itself is illustrated in figure C, where you can see it is just a combination of the mean of the predicted step and the observed step. So how does this play into the data assimilation that we did for Sandfire, as shown in this slide? So this slide shows the fire coverage error when we did data assimilation with barrier points and with just with conventional data assimilation, and in a case where there was no data assimilation that took place. So the green lines show the case where there is no data assimilation that took place. We just ran it through Farsight. You can see that the error, along with the mean, maximum, and minimum error, grows over time significantly and becomes uncontrollable. With conventional data assimilation, where we use the Farsight prediction step and the observation, but we did not use data points, we can see that the error, although it grows, it's still a little more manageable, a lot more manageable than when there is no data assimilation. You can see that the mean tends to grow and also comes down a little bit, but the errors, the maximum and the minimum, also tend to grow over time. Now with the barrier points included, barrier points or stationary points included in the data assimilation, you can see that the errors are actually a lot more controllable and a lot more easy to maintain. If you just take the mean into consideration, it rises and decreases. And if you take the maximum and minimum errors also, it is not as much as the conventional data assimilation or even the no data assimilation part of the analysis. So you can see very clearly that the error actually reduces quite a bit if you take data assimilation with the barrier points into consideration. So in terms of the contributions that this study has helped us with, is that we have included the uncertainty of the fire parameters by using ellipsoid for the confidence regions, and this has a very direct impact based on the density of the observations as well. We have been able to identify and learn that we can use stationary points and fire parameters to progress the fire parameters as predictions, and this significantly minimizes the error in the predictions of the fire parameter as time progresses. And along with that, we also progress the confidence regions using Farsight, which can be used as a priori of the covariance. And when we have high resolution of fire parameter states through ensembles and stationary points, we can use a Kalman gain adjustment to update or improve the covariance, which we can also call the posterior covariance. What helps the fire boundary predictions and simulations is that real-time measurements of fire boundary definitely helps to a great extent to predict how the fire progresses at further time, and inclusion of stationary points parameters as barriers in Farsight, which could just be points in fire that have not progressed because of firefighting efforts, or the topography does not allow the fire to progress. Using all this data will help us determine a better prediction. And proper use of uncertainty associated measurements also should be considered deeply, because that has a major role to play when you try to progress how the fire has progressed over time. That was the entire presentation. For more information, you can read the paper that has been published as well. And if there are remarks or questions concerning this project, or just in general about wildfire predictions, you can reach out to my professor Raymond de Calafon at the email ID that is given here, calafon@ucst.edu. Thank you.
Hi, my name is Tobias Finn, and I'm with the University of Hamburg and the Max Planck Institute for Meteorology. I'm currently a PhD researcher doing research on strongly coupled data assimilation between the atmosphere and land. And today I want to talk about the progress in a side project of my PhD. To be specific, today I want to talk in the next 30 minutes about how to stabilize unsupervised deep learning for data assimilation. So, why do we want to use deep learning for data assimilation? We want to use deep learning for data assimilation because nowadays we have small-scale forecasting models. So for example, forecasting models with forecasting convective precipitation and so on. And the temporal development of these forecasting models is very nonlinear, or often very nonlinear. And following on this, the involved model states in these forecasting models are also quite non-Gaussian. So for example, the cloud representation in models can be often represented by a gamma distribution, where we have the maximum of values for cloud and also another maximum of values for no cloud. And the number of values in between are lower in its distribution. Another problem is the question of how to handle nonlinear observation operators. Because due to nonlinear observation operators, we might have non-additive, non-Gaussian observation errors. So for example, if one would imagine that we have observations of rain, and so for example from rain gauges, and these rain observations are quite often only yes or no information. So these rain observations are often drawn from Bernoulli distributions, which are of course very non-Gaussian, and also the observation error is then non-additive. And deep learning can naturally handle these problems, because deep learning is based on deep neural networks, and neural networks can handle nonlinearities quite naturally. So another advantage of deep learning compared to classical data assimilation is that we have no local optimization as in variational data assimilation, and we would have no weight estimation as in ensemble Kalman filters. So we would have a global optimum or a trained neural network, which is then applied for data assimilation. And so one can say, or one can expect that data assimilation based on deep learning is faster than traditional data assimilation. So, but there's a problem, because normally neural networks are trained based on supervised learning, but for supervised learning we need to know the truth, and the truth is unknown in data assimilation. And so we cannot use supervised learning, and there are different options. So for example, one could train a neural network to emulate the analysis of existing data assimilation algorithms, but then we have the problem that these neural networks cannot be better than these traditional methods, and of course we want to use neural networks to handle nonlinearities, non-Gaussianities, and so on. So one way to handle this would be to use unsupervised training or unsupervised deep learning. And in the next slides, I will show how we can use unsupervised deep learning to train these neural networks. But as a first step, we have to cast data assimilation as latent variable model. So what is a latent variable model? A latent variable model means that we have a model where we have two different kinds of variables. The first variable are the latent variables, which are unknown, and then we have observations of these latent variables, and then we have a connection between these two kind of variables. In data assimilation, this connection is called observation operator. And so now we have these observations, but we want to get the a latent state, so a latent variable out of these observations. So we want to get the inverse of this observation operator. And as I said, we want to use deep learning for this. So one way to do this would be to use the observations, define a neural network. Let's call it here, not f von x, g von x. and then we can train our neural, and then we can use this trained neural network to get the inverse of the observation operator. In data assimilation, we have an additional input to it, because in data assimilation we know the prior. The prior is often is in data assimilation often a previous old forecast run of the forecasting model, and so we have an additional input, the prior, which can be also used, and then we have not only a function of the observations, but also a function of the prior. So now we have defined our function, how to get our latent variable from our prior and our observations, and now we have to train this model, this deep neural network. And one could think of using the variational data assimilation cost function to train then the neural network based on this variational data assimilation cost function. But the problem is here that we have then a Gaussian assumption in it, and also there might be a linearity assumption. And so we do not want to make these assumptions, and so we have to rely on another method. And this other method is also called variational inference. And in variational inference, we are minimizing the so-called, or maximizing the so-called evidence lower bound, or minimizing the negative evidence lower bound. And in variational inference, we try to minimize the Kullback-Leibler divergence between the approximated posterior. I'm defining it here. So the approximated posterior is then the output of our neural network, and we want that this approximated posterior is similar to the real posterior, to the real unknown posterior. And one can show that this Kullback-Leibler divergence is then proportional to the negative observational likelihood, negative log likelihood of the observations, and the Kullback-Leibler divergence of the posterior to a prior. So as I said, this prior is given by an old forecast run, and this includes, this first term includes the observations, and so we have actually two different terms which resemble the traditional data assimilation cost function. We have a first term, the negative likelihood of the observations, and then a nudging term to the prior. And one can show that this is in some kind a Bayesian generalization of the traditional data assimilation cost function. And as I said, it is easy to show that the classical data assimilation cost function is in some kind of special case of this. So if we simply assume that the involved distributions here are degenerated, or if we assume that the posterior is a degenerated Gaussian state, then and additionally assume a Gaussian prior and a Gaussian observation error, then we get the variation data assimilation cost function. And as I said, this is a natural cost function for fully Bayesian data assimilation, because we have an additional term which tries to optimize the entropy of the posterior. And one can also show that the ensemble transform Kalman filter is a special case of this, for a special case and the optimal solution in Gaussian and linear settings. And so, in some sense, we have now a generalized cost function for Bayesian data assimilation. But the problem is now that to optimize this Kubrick-Leibler divergence, we need an explicit distribution of the prior, and the prior is often given only by ordered model forecasts, and so we would need to assume in some sense a Gaussian distribution or something like this. And so another way would be to approximate this Kubrick-Leibler divergence, and we can approximate this Kubrick-Leibler divergence by another neural network. And so we train another neural network which outputs the Kubrick-Leibler divergence between the posterior and the prior. And the nice thing is that if we can train this neural network with a so-called adversarial training. So this neural network gets during training either the prior data or the posterior data, and then outputs the probability that the given sample is a posterior sample. So this is then and we can then train this neural network by the so-called binary cross entropy, where we define that a prior sample should have a probability of 0, a posterior sample should have a probability of 1, and then one can show that the logit output of this neural network equals this Kubrick-Leibler divergence. This sounds nice, because now we only need to have samples of the prior and of course samples of the observations, and we don't have any more an explicit assumption about the model distributions. But there's a problem, because we have difficulties to scale this up for high dimensions. So here I plotted the Kubrick-Leibler divergence between two Laplacian distributions with 5 dimensions here, and we can see that the real Kubrick-Leibler divergence is 4, and the approximated Kubrick-Leibler divergence is also around 4 after some iterations. So this looks quite nice in 5 dimensions. But if we scale this up to 200 dimensions, then we get a huge gap. This huge gap is related to the cost function, because if we plot the cost function of the binary cross entropy, then the binary cross entropy has a logarithmic dependency on the Kubrick-Leibler divergence, and so for higher dimensions it is more difficult to get the right Kubrick-Leibler divergence, and so small changes then have a huge impact on the gradients and on the Kullback-Leibler divergence. And so it is, for this cost function, it is very difficult to scale up to high dimensions. So how would we now enable high dimensional adversarial training for data assimilation, for implicit data assimilation? And for this, I created a checklist for candidates. We have here two different points. The first point is that the discriminator, so the second neural network, which approximates the Kullback-Leibler divergence, should directly approximate this Kullback-Leibler divergence and output this Kullback-Leibler divergence. And this is given for the standard binary cross entropy loss. So this is also related to the so-called generative adversarial networks. And then the loss function of this generative adversarial network should be linearly proportional to the Kullback-Leibler divergence. And this isn't given in the standard GAN loss. As I said, we have a logarithmic dependency, and so here we have the problem. And now one can ask about the so-called Wasserstein GAN. Wasserstein GANs were developed 3 years ago, and were quite successful to stabilize this type of training for high dimensions. And so the Wasserstein GAN is defined as the difference between the discriminator, or it is here now called critic output of the neural network, and it tries to maximize this cost function. So it tries to maximize the output of given the posterior samples, and tries to minimize the output for the prior samples. So this paper of Ajovsky et al. Laid the theoretical ground on this, and it is based on the so-called optimal transport, and has quite nice properties, but there's a small caveat, because on one hand we want to maximize the neural network, but we want also that the so-called Lipschitz norm of the neural networks is below 1, so that the neural network is bounded, and this constrains, of course, the neural network. And another caveat is that this cost function does not minimize the Kullback-Leibler divergence or something like this. So it is in some sense, yeah. It is in this written type unuseful for our purpose. So and instead we can apply a trick. We can switch over to the so-called F-Wasserstein GANs. In the F-Wasserstein GANs, we have, again, minimum or maximum, it does not matter. I will write here the minimum. Again, we have a Lipschitz constraint of 1. And then we have now, because we want to minimize this, or we can also write we maximize this. As I said, it does not matter. Maximize the expected value given the posterior samples of the discriminator output, minus the expected value given the prior samples of a new term which I will explain in a few seconds, and the output of the neural network. This new term is related to the density ratio between the posterior and the prior, and one can show that the output of the neural network approximates the Kullback-Leibler divergence if this term equals to a normalized energy. And now we can use this cost function to train our neural network. And the nice thing is now that this term should be as low as possible, or if we minimize it, as large as possible. And this term should be maximized. And this type of adversarial training then can be used for higher dimensions. So we have still a gap, but this gap is lower than before. And this gap is related to different things. So on one hand, we have a small bias introduced in this type of approximation. Then we have regularization involved. Why we have regularization involved? Because here we have this Lipschitz constraint, which we need to satisfy, and this regularization leads to an unparameterized neural network. And so, but nevertheless, this gap between the approximated Kullback-Leibler divergence and the real Kullback-Leibler divergence is smaller than for the original cost function. And if we now show the loss function, then one can see that this loss function is proportional, or not proportional, but yeah, is in some sense proportional to the original Kullback-Leibler divergence, and so we satisfied both checkpoints in our list. But now we have a problem with this Lipschitz norm, with this Lipschitz regularization, and so the main question is now how to enforce the Lipschitz 1, or how to enforce that the neural network is Lipschitz 1. So and we tried this out on the Lorenz 96 model with a quite nonlinear temporal development. So we assimilated observations every 12 integrations at 20 different randomly distributed points, and then we generated a training data set. We took the background from an existing LETKF cycle, and then trained our neural network on this given background, and the observations. And then we trained our neural network by this F-Wasserstein GAN, and we had 1,024 training samples. And we had an observation error of 0.5, a Gaussian distributed observation error. And here we can see the arrow, the RMSE in an evaluation, or yeah, the RMSE compared to our nature run for our neural network and for the LETKF. And we can see different things. On one hand, we can see that the RMSE of the within the training data set and within the testing data set equals. So we have no overfitting during training. The ensemble spread is automatically tuned, but we have still in some kind a gap to the LATKF, and this gap is related to the problem that we do not use any ensemble information in our neural network. So we assimilate every ensemble member independently in our method, and so the next step would be to incorporate in some sense ensemble information into it, such that we get a dynamic neural network depending on the current ensemble state. And with this type of data assimilation, we get a similar error magnitude as the ETKF, so as an ensemble Kalman filter without localization. And as I said, we don't need to tune the spread of the data assimilation because it is automatically tuned by this cost function. So here again we can see the red lines are the neural network. The bluish lines are the ETKF, and this is for an unobserved grid point, and we can see that the neural network is nudged towards the truth as the ETKF. And then we can estimate the covariances between our observations and between a grid point over our whole testing data set. And on the left side, the covariances of the increments is shown, and on the right side, the covariances of the error are shown. And one can see that we might have a problem with spurious correlation because we have here over values in the covariances which are not in the error covariances, and so we might need in some sense localization for this as in an ensemble Kalman filter for this type of data assimilation. So we probably need an additional regularization term which localize our increments. And then we also try to this kind of data assimilation was optimized globally over a training data set, and then we can optimize this neural network also locally. So we use then the global optimized parameters as starting parameters, and then optimize with our cost function for a single training data for a single training step, and then we get this RMSE, and we can see that we can improve by local optimization our data assimilation as in variational data assimilation, but we have here still a problem of in some kind overfitting. And we don't know yet, or I don't know yet, why we have this kind of overfitting, but yeah, it is work in progress, as I said. So, as I showed, I showed here theoretical adaptations of adversarial training for data assimilation, and with this we get similar performance to the ensemble transform Kalman filter, and with this Wasserstein GAN we stabilize this type of training for data assimilation, but the main difficulties are now the architectural decisions, so how to incorporate ensemble information, how to enforce localization, and then Another question would be, can we learn this type of neural networks in an online setting? So can we learn this during application? So what should you take home? As I showed, we use now the so-called F-Wasserstein loss function to stabilize the training of deep neural networks for data assimilation. And with this, we get a similar performance to a tuned ETKF, and local optimization can help to improve the training, as I showed here. And as I said, the open questions are now how we can use ensemble information during inference and how to localize the increments during training. Hopefully this will be published in this year, or will be submitted in this year to nonlinear processes in geophysics. And if you have questions, please feel free to contact me, and thank you for your attention.
Hello to everybody. My name is Data Assimilation. I come from Poland, from Krakow, from AGH University of Science and Technology. I am the leader of Complex System Group, and this research was paid as a collaborative research between AGH, Gaussian University, and Bergen University. Today I'll have to speak about supermodeling, model ensembling, but from the perspective of data assimilation. This is a short agenda of my talk. So the main motivation of the talk is there are limits in complexity of classical data assimilation algorithms and parameter matching to big over-parameterized dynamical systems. I'd like to speak about model ensembling, about supermodeling. I'll speak what is the difference between such a, say, regular model ensembling and supermodeling. We show how we can use supermodeling for just improving modeling performance and using supermodeling as a meta procedure for data assimilation. As the examples, we have two examples. The first one is the heavy model. This is social-economical model, which is described by a set of ODEs, and the council model. And the conclusions, I'd like to summarize our findings, and we'd like to say something about future work, and we show very quickly preliminary results. Let me start from the SuperNet. SuperNet is just ensembling of neural networks in machine learning. Every model is a data model. This data model is represented by the neural network. So instead of training the whole neural network, we have to train it in a very short time. We can do this several times, and then on the base of data fusion, we can say produce the decision of the ensemble. In this ensemble, each submodel is working independently, and at the end, the decision is made. You know. However, we can do this in a different way, like this. So we can use the last layer as the coupling layer between the model, and instead of just using some rule inclusion, we can train this the last layer, and generally we can obtain much better results than using a standard approach to model assembling. In this case, we have now just independent decision. So this is some sort of consensus between models. Okay, this is say an example of the results obtained by using SuperNet. As we can see, we need just 10 epochs to get better results, or the same results as we can get after 75 epochs. This is also clearly visible that supermodeling is much better than just majority voting and softmax voting, which represent regular decision fusion. Even for the model which is completely trained, we have here the six submodels. So supermodeling is much better than a regular ensemble. So let's go now to the dynamical system. So every dynamical system can be treated as a model with parameters, and these parameters have to match the data. So this is a bit similar to neural network and matching the weights in the neural network. But for such a formal models, which are represented by a set of ODEs or partial differential equations, the number of parameters shouldn't be large. The problem is that complexity of data assimilation algorithms used for models of dynamical systems is exponentially with the number of parameters. So our idea is similar as this one shown before for neural networks. We use such a classical data assimilation algorithm for short pre-training of a few instances of the over-parameterized Bayesian models. We couple them via a few metaparameters in a single supermodel, and then we match the metaparameters of the supermodel by using this classical data assimilation algorithm. The problem is that the number of the metaparameters is much, much lower than the number of parameters in the baseline model. So first, we define the supermodel as an ensemble of m imperfect submodels. They can be also heterogeneous models, completely different models. But in this talk, we'll speak about submodels as a same, which is based on the same baseline model, but with different parameterization. So we can have m dynamical systems, and these m dynamical systems, instances of the same model, are synchronized with each other and with reality via couplings. So some number of variables and observed data xgt. In this slide, we can see how it looks like formally. So the submodel can be described as a set of ODEs, yeah, because we have few submodels. The dynamical variables are coupled through the coupling coefficients, and the same dynamical variables are coupled to the data by the coupling constant tensor k, and the model are synchronized by the tensor c. We are trying to find this coupling factors, minimizing the root square error, like here. Okay. Usually, this is the approach to supermodeling, which was presented in Sumo project in 2012. The main idea of supermodeling is that when we have say a few submodels, which are represented by this, say two submodels, two trajectories, yeah, and these trajectories are penetrating some regions of the parameter space. After coupling, we can move the supermodel, which consists of these two models, to a completely different subspace of the parameter space. And we can direct it to the attractor, which is represented by the data. This is the scheme of our supermodel. We have a few submodels. Each of submodel is the same from the formal point of view to the other submodels, but all the submodels have different, have the same set of parameters, but the parameterization is different. I mean, different values of these parameters are taken for the three different models. The models are coupled from these two in here, two variables, for so-called coupling factors. Yeah, and additionally, the model is coupled to the ground truth data. Supermodel was used earlier in climatology for a set for ensemble of different very big atmospheric ocean land models, and it appeared that the supermodel works much better than the standard multimodal model, standard assembling, giving much accurate results. So here we propose to attack this problem from the different side. I mean, we have few models, but these models are not the perfect, imperfect models, but they are pre-trained for a very short time, computational time, by using a classical data assimilation procedure like ABC procedure, or for DVAR or other algorithm based, for example, on common fraction filter. So after pre-training, we couple these models, and we couple these models in such a way that we don't, like before, minimize the square error, but we use the same, another, it's your decision, classical data assimilation procedure to match the parameters of the supermodel, coupling parameters. I mean, the parameters representing, yeah, but these values. See it, because we have not this one, this this expression we remove from our approach. Okay, so after coupling, we trained our supermodel, the coupling factor of the supermodel, to get the ground truth data. So comparing to the previous approach, we removed this nodding factor, which say couples the models with the data, but we have just this one factor. This is a synchronization factor, and this short, smaller model we trained using, for example, approximated Bayesian computations, ABC model. This way, we can take a few of the best results from ABC. Each of them can represent an instance of the submodel, and we can couple this submodel not through all the variables, dynamic variables, but just one variable, which is the most sensitive variable. I mean, the variable which small change or we made big changes in the behavior of the file model. Okay, let's go to the examples. The first example is the social-economical handy model. Handy model is a substantial extension of the predator-prey system. It describes it is described by 4 dynamic variables. One represents commoners, second elites, nature and wealth. So commoners and elites produce wealth, elites eat it, and the cost of nature, of course. The model is described by 14 parameters, including initial values for dynamic variables. We use this model for our research because it is not big, but has a lot of parameters. So we need to match these parameters on the basis of some data. Of course, we have no real data, but we can generate them. This is the typical plots, time series for commons, nature, elite, and wealth. We divided on 3 intervals. The interval, which is in the middle, we took as the ground truth. Yeah. So we sample this curves, and the samples we use for predicting the behavior of the system forward and backward. This is just one result of our prediction. And more is presented in our paper and muscle physics of Mr. Sandera. As we see, for a given time budget, this is the interval which is responsible for teaching, for training. So we can see the very good approximation of the extrapolation of the results forward, and not so good, but better than for a single model. So for the classical data assimilation procedure in the backward prediction. We use also, as an example, the Causal dynamics model, which is a predatory prey system, and which describes tumor dynamics during anti-cancer therapy. But the evolution of also for dynamic variables. First, we have concentration of anti-cancer drugs, the concentration of proliferating cancer cells, the concentration of quiescent cancer cells, and mutated quiescent cancer cells. I would like to go into details, but you have in the left top part of this picture the equations which describe this process. We see here that the cancer is growing. So after diagnosis, we have some treatment for cancer. The size of the tumor is decreasing, and after some time it grows like here. Okay, so because of this mutated cancer cells. By the way, MTD is mean tumor diameter. Here we have time. Okay, having this set of equations, we are trying to find the most sensitive variable. It appeared the most sensitive variable is just concentration of tumor cells. However, we checked also 10 experiments, other dynamical variables. We see that the best is dense connection between submodels, but for P, we have this yellow line. It's okay. By the way, we see that for, say, single model, the error for a given time budget is the highest. So we have also 3 models, these 3 models, and 4 dynamical variables. Only one variable is used as a connection between these 3 models. Because our model was completely naked, I mean, we have no idea what these parameters, what values will have these parameters. we approximate our model to real data given in the paper by Riba et al. Published in 2012. Much more since the data, but we are concerned about just say approximated values of these parameters. We made some approximation. We use classical data assimilation procedure to get the first approximations of our parameters. This is what you obtain for simulating, for predicting the treatment, assuming that we know the dynamic of the growth in this small interval. So on the base of this interval, on the base of these values, we say with the first step, I mean, we pre-trained our models, submodels, and then we coupled the three submodels as a supermodel, and then we trained using classical data assimilation procedure the coupling coefficients of the supermodel. So what we get, I think that this right-hand side panel is much better because it's directly seen how error we obtain for the single prediction, single model prediction, of course, in the same time budget, and for the supermodel. We see that the supermodel is superior comparing to the single model in which we use the data assimilation procedure. So there are conclusions. So we can say that supermodeling can be recommended as an efficient and accurate meta procedure for data assimilation and parameters matching. It works in the following three steps. The first, we pre-train a small number, like 3, 4, of baseline models using classical data assimilation procedure, like ABC, SMC, 4D-VAR, etc. Then we can couple the models through the most sensitive dynamical variable, just one, creating the supermodel. And then we can use a classical data assimilation procedure for training the latent parameters C. The future work, which will concern the big model of cancer, we use 3D supermodel of melanoma for prediction of cancer dynamics after treatment by using real data. That we have some preliminary results. First, we developed a very efficient model of cancer, model of melanoma. As you see, now we have much more. We have 8 dynamical variables, and we have much more parameters than before. More than 40 parameters, including initial values of dynamical variables. So we modeled skin, and we modeled the evolution of the tumor in skin. The model we use, this is a single-phase model, but the single-phase model is connected. Single-phase model is a continuous model, and we have to connect it with this model with a discrete model of vessels. So the direct interaction between the tumor and growing tumor and vessels should be seen and should say influence on the tumor growth. Yeah. So this is our supermodel. As you see, we have some prototype. We select the best and diverse solutions. Solutions of what? Solutions of the application of the standard data assimilation procedure to this model. So having this submodels, we use the supermodel, and we trained the supermodel, just 3 coefficients, not 40, 3 coupling coefficients. We trained them on the basis of data. We obtained some preliminary results, just comparing the different kind of supermodels. Now unfortunately, we have no real data. We have to produce first the data from say baseline model and trying to find the parameters of this baseline model. At the end, I'd like to show you my group. We are collaborating. I'm just saying we because I am a leader of complex system groups. So Adam Krusek is from my group, and also Leszek Siwik is also from my group. We collaborate with very experienced climatologists, Gregory Duane from Boulder University. He's working in the University of Bergen, and with my former student, MSc student, Maciej Sendera, who is the first author of the paper, and who is now working in Jagiellonian University in Krakow. Thank you very much for attention. I'm just waiting for the questions to my talk.
Hi everybody, my name is Giuseppe Brandi and I am a PhD student in applied mathematics at King's College London. Today we'll speak about a paper I wrote with my supervisor Tiziana Di Matteo, and it is related to multidimensional data. This paper is a follow-up of other 2 papers we recently wrote. One of those has just been published in the Journal of Computational Science, while the other one is just been submitted. So all those papers has in common the analysis of multidimensional data using tensor approach. So what we try to do here is to extract information from multidimensional data using tensor analysis. The motivation is given by the fact that a lot of multidimensional datasets are available nowadays. However, what we usually do, we use matrix and vector analysis to extract information from those datasets. And this poses a huge drawback since we lose a lot of information. In particular, we lose all the higher dimensional links that you have among the dimensions. Another issue is that using vector or matrix form of those objects will increase exponentially the number of parameters. And we need a parsimonious technique which gives us the opportunity to model the data without oversimplifying models. In fact, what we usually do, we use some criteria to eliminate some of the variables from our regression or analysis to simplify the model. And the final motivation of this series of works is to bridge the tensor research community with the economics and finance one. In particular, this paper comes to answer some of what we see challenges and issues in the network community. Usually when we work with financial networks, those networks come from correlation matrices or are based on symmetric dependency measures. And this will hide all the asymmetries that can be in the data and between the agents that we are trying to model. Another issue that we see is that networks are usually constructed using contemporaneous information. So all the interconnection that we are going to measure neglect all the possible delayed cause effect. And this is specifically the case in finance, where usually the connections are a little bit delayed. So there is a time cause effect between variables. So what we want to answer is, can we estimate a causal in time multilayer network directly from the data? And the answer that we try to give here is yes, and we propose a method which uses tensor learning to estimate this multilayer network. But what are tensors? Tensors are a multidimensional arrays. However, they are not just a concatenation of matrices or a three-dimensional object of data. They have their own structure, their geometrical structure, and for this reason, they have a lot of information which can be extracted using tensor decompositions and tensor analysis. Tensors are just generalization of scalar vectors and matrices. In fact, scalars are zeroth order tensor, vectors are first order tensors, while matrices are second order tensors. When we have more than 2 dimensions, we just call them tensors. In economics and finance, we have a lot of examples of tensors. We have panel data or longitudinal data where we have individual variables in time, or we can have time series of networks or time series of covariance matrices, and those are all three-dimensional objects. But you can have also more than three-dimensional objects, and they will be still tensors. The literature on tensor is quite vast, but all started with Tucker in 1964, when he was trying to work on a psychometric model to extract information from patients. After that, a lot of papers came out, and nowadays we have a lot of tensor methods and tensor analysis in the literature, especially in machine learning, artificial intelligence, and network analysis. As we were saying before, everything started with Tucker. Tucker, in 1964 and some paper afterward, wrote a model which nowadays is called Tucker decomposition, also called higher order singular value decomposition, which uses the algebraic structure that a tensor has to decompose the data set and to provide information on the latent space. So we do what we usually do in matrix form with the singular value decomposition, and we try to factor the tensor in smaller objects. So what Tucker was doing, he has a tensor which has 3 dimensions. One dimension was devoted to the patients, another one to some variables of the patients like blood pressures, sugar in the blood, and other variables, and the time at which the patient was seen. So when you decompose this tensor in a small core tensor and other 3-factor matrices, what you get is that the core tensor just gives the links among the different dimensions. The first factor matrices is devoted to the patients, the second one to the variables, and the third one to the time. So we'll give you some time evolution of one of the factors. However, the tensor, especially the Tucker decomposition, can also be used as a parsimonious tool. In fact, if you think of this tensor here as being a 10 by 10 by 10 tensor of data points, those can be approximated by a small core tensor, let's say a 2 by 2 by 2, and 3 factor matrices, which are 10 by 2 in each, which multiply in each mode the core tensor. This will generate a 68 data points approximation of 1,000 data points. Of course, the approximation will be driven by some criteria, which will need to be used in order to decide which is the number of the Tucker rank to be used. In some cases, this comes from theory. In other cases, you will have to use data-driven approaches. Mathematically, the tensor is written as the n-mode product of the core tensor, and each of the factor matrices will multiply one specific dimension of the core tensor. Now, the tensor regression literature is quite new. The first paper came out less than 10 years ago, and it was more in the neuroimaging analysis. However, all the papers that came out were all missing some point. In some cases, the model were not parsimonious. They were quite big, and they were not fully tensorized. In other cases, the tensor were only in the dependent variable or independent variable. In some other cases, especially the last one here, the tensor is just made as a concatenation of matrices. And in fact, this will create independence between each mode by construction, which is something that we don't want to have, since we want to extract information across the dimensions, not just making them independent by construction. So for this reason, we recently wrote a paper in which we have a fully tensor regression, in which both the dependent and the independent variables are tensors, and even the slope or regression coefficient is a tensor. What we have here is for this specific application is a tensor autoregression. This means that the y, the dependent variable, is a set of financial variables. In our case, it's a three-dimensional data set, while the independent variable is a lagged version of our dependent variable. So it's it has one lagged, it's a lagged variable of the y variable. So b, or beta, is the coefficient tensor which connects the two tame points. So we are trying to find a coefficient which give us the causal relationship, causal in time, between the variable at one point in time and the next point in time. So what we are interested to learn is this coefficient here, which will represent our multilayer network. To estimate this coefficient, we use the standard least square methodology, and we use the minimization of the sum of square residuals. However, the beta coefficient is quite huge. So to have a parsimonious modeling without dropping some of the variables, we build a parsimonious Tucker tensor regression, which means that we substitute the beta parameter here with its Tucker representation. Now, as we saw before, this can be the dimension can be really severely reduced, but this will need to be done with some caution, since the smaller the rank that we impose, the lower is the precision. So what we have here is just the same equation, but with the Tucker representation instead of the beta. This is a nonlinear optimization problem which cannot be solved in the standard way. So we need to have an iterative algorithm which solve iteratively the problem. And we can use the alternating least square, which has become one of the workhorse of tensor analysis. Here we have a sketch of what the algorithm is. So what we have is that we start from a standard random tensor values for the Tucker decomposition. We have a random core tensor and some random factor matrices, and then we use the least square solution of each component. So each of the factor matrices and also the core tensor, using the fixed value at the previous iteration of all the other factor matrices and the core tensors. And we use our data information to find the least square solution. In a recent paper, one of the papers I told you about before has the explicit solution of all those least square problems, so that can be directly used in a code to implement a tensor regression. However, the tensor regression is prone to overfitting when there is intra-mode collinearity. So we need to have a shrinkage estimator to have a stable solution. So we use the ridge regularization, and we introduce this lambda parameter which regularize the estimation. The stronger is the effect of this lambda, and the higher is the bias on beta. So what we need to have is to have a lambda which is data driven. We need to choose a lambda which give us a stable solution, but which doesn't bias too much the solution. Now let's go through the financial application. As said in the beginning, we are interested in finding and analyzing a multi-layered network of financial data. To do this, we will use some data which are prices, volumes, and future volatility measures, as the implied volatility at 10 days and 30 days. And those data should reflect three different aspects of financial risk, especially market risk, liquidity risk, and future volatility risk. What we want to see is how those factors are related among them, and also within each of those variables. Each of those variables will represent a layer in our network modeling. The data that we use are daily data on stocks taken from the Dow Jones. What we had is to find some information from this data set which was needed to compute this multilayer network. So what we did was to employ a fractional differentiation instead of the standard unitary differentiation in order to balance stationarity and the memory in the data. In fact, when you differentiate your data, you are losing a lot of memory from your data, and so you're losing a lot of information. However, we need to have stationary data to build and to use our models. So what we did, we used fractional differentiation with different order, fractional order of differentiation, and we ran a stationary test to test if those data were stationary. And what we found is that with a value of 0.2, all the data were stationary. So we are losing really a low amount of information while still having stationary data. Now, we need to choose two parameters in order to estimate our model. The first one is the rank, the Tucker rank that we want to impose to our beta. And the second one is the shrinkage parameter. For the first one, we decided to use a full rank specification since we didn't want to have the reduction of independent links as you usually have in factor analysis. For the second one, we decided to use as a criterion the predicted R squared. So we run our model with different values of shrinkage and computed the predicted R squared. And the best one was given by the lambda parameter equal to 0, so no shrinkage. Now, how I already said before, our beta coefficient will represent our multilayer network. However, this multilayer network is usually fully connected. To eliminate some of the redundant and retrieve only the important information, we use the Poda filter of Marcazzoli and Levan, and we use a parameterization which left out only the 10% of more relevant links and removed the 90%. To analyze this network, we then use two different measures on multilayer networks, which is the interlayer associativity and the edge overlapping. The first one will give us if two layers are giving in the same directions, so they are positively correlated. And the second one will tell us if the proportion of edge which are overlapping across two different layers, and will tell us if two layers have common connection behavior. What we can see from the results here is that, for example, prices and historical implied volatility, they have a huge overlapping edges, a huge proportion of overlapping edges. However, as we can see from the associativity matrix, they are negatively correlated. So it means that they have a lot of the same links, but they are going in the opposite direction. And this is something that is quite true in finance, as it is a stylized fact that prices and volatility are negatively correlated. Another thing to see here is that the two-measure volatility has a huge correlation, a huge proportion of overlapping edges, and not surprisingly, they have also a good correlation between the two. So they are quite similar, even if they are not the same. They are not equal. In fact, they try to give information in two different aspects of future volatility. Finally, we want to let you see the graph representation of the multilayer network. And what we can easily see, for example, is that the volumes layer has a lot of interlayers connections, while fewer intra-layer connections. This means that the average shocks that we have in the volume, so liquidity risk, doesn't go through the volumes layer, but mostly it drives the surge of volatility and diminishes the prices dynamics. So as we can think, and we also know in finance, sometimes liquidity risk go through the increase of volatility and the decrease of prices, rather than just go through other liquidity rather than just be matched to other liquidity issues on other stocks. So let me conclude. What we did in this paper is to build a methodology in order to estimate a multilayer network using tensor learning. We proved that the interconnection between the risk factors analyzed have been quite good, and they represent some real financial mechanism, which is quite useful as a tool for risk management. What we want to do after is to extend this procedure to a fully dynamic framework, which means that we want to have a multilayer network which is not static, but which moves in time. This will give us the changes that you have in time of the multilayer topology. And secondly, we want to analyze this multilayer network under different market conditions, which is it's also related to the previous point. What you want to do is to analyze the estimation of this model of this multilayer network in the stress period and in calm period, and see which are the differences that you have in these two multilayer networks. Okay, so this is all from me, and thank you very much for your attention. Bye.
Hello, my name is Rossella Arcucci. I'm presenting here Neural Assimilation, a work in collaboration with Lamia Mutik and Professor Rickeguo. This work has been done in the context of the Data Learning Working Group at Data Science Institute, Imperial College London. In the group, we mainly focus on a few questions. In this presentation, I will focus mostly on the point of achieving both accuracy and efficiency to improve estimations or prediction. The point is that we right now have a lot of available data. These available data are from models, very high resolution models. The point that in order to improve the accuracy of the forecasting, we couple those models. And also, we have right now a lot of available observations from different fields in different applications. So what's the point? The point is that if we try to make a prediction, to make a forecast, we have our initial condition. Let's assume that we have this forecasting model, which can be a black box, like a system of PDEs or a machine learning model, any kind of model. Let's assume that it's like a black box. So the problem is that the numerical solution is affected by several errors. First of all, there is the error given by the point that you are simplifying the reality using mathematical equations. So there is simplification error. Then these mathematical equations have to be solved numerically, so there is a discretization error. And finally, this discrete problem should be solved on a computational architecture on a computer. So it means that there is a propagation of the round of errors. Or these errors are propagated on errors on the data. If we consider the backcore error analysis, we can say that all these errors in the data are propagated in the solution for several reasons. The parameters that propagate the error are given by, depends on the condition number of the problem, on the algorithm you are solving to use, you are using to solve the problem. But sometimes, as I was saying, this forecasting model is like a black box. Imagine an operational center where they have these huge systems to make forecasting. You cannot really, sometimes from a data science point of view, you cannot modify the system. So what we can do in order to reduce the error in the solution, we can work on the reduction of the error on the data. How to have it? How to do that? To do that, we use data assimilation. Data assimilation, if you try to Google it, you will find like several different definitions. For engineers, usually it is defined like a filtering problem. For mathematicians, it is usually an ill-posed inverse problem. So let's say, what is data assimilation?
We are all familiar with the butterfly effect. A small change in the weather in one part of the world can have huge consequences in another. How can we detect such changes early on so that we can act better and sooner? Scientists are developing numerical models that deal with this uncertainty and make forecasts more accurate. They do so using data assimilation, a methodology that combines observed measurements and numerical predictions. Take a weather forecast. Using an initial data set of temperature and air pressure measured in a region, researchers develop a numerical model that predicts how they will change. This is challenging because airflow is chaotic and many variables need to be included in the model to predict this change. This also means that the model's prediction will have a high level of uncertainty. To limit this uncertainty, real-time data is collected and input, or assimilated, into the model. Researchers observe how much the real situation differs from their numerical model and adjust it to make the forecast more accurate and reliable. The maths behind data assimilation can be applied to a variety of research topics, from atmosphere and climate changes to vehicle design and health management. The Data Assimilation Laboratory is just one of the multidisciplinary labs that make up the Data Science Institute. To find out more about our work, visit imperial.ac.uk/data science.
So, just to summarize, you have your data initial condition. You use the data in order to make in the forecasting model in order to make a forecast. Then you have, for data assimilation, other data, external data, we call observations, observed data. You can merge those two data with data assimilation, computing a new initial condition that can be used for the forecasting model in order to compute a new forecast more accurate and reliable. So someone could say, why we don't just use observations? This is because we should solve a problem, an ill-posed inverse problem. So how can we face this problem? So we have these 2 points. We have the forecasting model, the solution of the forecasting model. We have the observations, and we have these operator, these mapping that convert the forecasting data into observations. And so what we have done this M, we have done this H, and we have this ill-posed inverse problem to solve. In order to solve the inverse problem, ill-posed inverse problem, we can use a Tikhonov regularization model. The Tikhonov regularization model consists in minimizing a function like this, where R and B are the observation and the background error covariance matrices that are like weights of the error in the data, let's say the distribution of the error in the data. So there are 2 different kinds of data assimilation, which are including time as a variable or not including time as a variable. In the second case, where you are not considering the time as a variable in the data assimilation process, you have a 3D data assimilation. If you are considering time, then you assimilate observation in a time window. Then you are then solving a 4D data assimilation, where the 4th dimension is the time. From the Tikhonov regularization, depending if you want to solve the problem minimizing the cost function, or if you want to solve the problem solving normal equations, you can find most of the data assimilation technologies, most of the data assimilation methods. For example, 3D bar, 4D bar, Kalman filter, optimal interpolation, and extended ensemble Kalman filter. So the point that we focus on mainly is that data assimilation then is used to improve the accuracy of the forecasting. And it will be great to use data assimilation as much as you can. The point is that data assimilation is a process, is a model computationally expensive. So what happened? You have a time window, you have some observations, you try to assimilate this observation, then you stop, you start a new process. And this is computationally quite expensive. So scientists worldwide are working on the reduction, trying to reduce the computational time of data assimilation. So if we consider, let's say, a general data assimilation algorithm where this equation 7 can be both for a Kalman filter or a variational data assimilation, doesn't really matter. This is just the Tikhonov regularization function. Then most of the, let's say, scientists worldwide are mostly focusing on the improving of the efficiency, focusing on the dynamical system. So, for example, replacing the dynamical system with a data-driven version of the dynamical system, so an emulator of the dynamical system, or on the background error covariance matrix, which is, let's say, a huge problem in the data assimilation process because it's a huge matrix and also ill condition. And so there are mainly the main works are on these 2 points. And we also at Data Science Institute worked quite a lot on these points. But all these new methodologies or these improvements, these new formulations can be introduced at several levels of the mathematical stack, obviously from the system to the algorithm. Usually, they are introduced at the level of the algorithm, sometimes at the level of the numerical model. But there is this famous quote of Alan Perlis for programmers that says, adaptive old programs to fit new machines usually means adaptive new machines to behave like old ones. And this is true. Because, for example, if you consider when we started to use parallel computing, and if you try to run a sequential algorithm on a parallel machine, you are just using the parallel machine like a sequential machine. So you have to modify the models. You have to work on the high level of the mathematical stack in order to really have benefit of the novelties. What's the novelties in our case? The novelties in our case are the new data sets that we have, that in past we didn't have so many observations, and we didn't have the observations so sophisticated and full of meanings. So if we continue to use old programs to fit the new data sets, actually you cannot have the benefit that we can really have if you start to reformulating some of the models from scratch in the high level of the mathematical stack, for example, reformulating some mathematical models. Here is where neural assimilation is. What is neural assimilation? It's quite simple, a simple idea. Neural assimilation is a coupled neural network made of two recurrent neural networks. The first one is trained completely on the forecasting data. The second one is trained on the forecasting data and the observations. The particularity of this network is that there are these two recurrent neural networks coupled with a weight. So it means that the second neural network is at each time step is taking the information from the previous one, transferring the weights. These are the questions of this coupled neural network. More informations are provided in the paper. This is the loss function that we use for the back propagations. And it can be proved that neural assimilation produces a solution of an optimal interpolation. An optimal interpolation is a simplified version of Kalman filter, where you have the covariance matrices fixed and you don't propagate the data using the forecasting model, so everything is fixed. So it's a first step, and you can have an optimal interpolation using this network. In order to implement the idea, we used an LSTM. Why an LSTM? First of all, LSTM is a recurrent neural network, but the main point is that LSTM is quite simple to be coupled. So it's simple to, because it is designed to contain information from outside. So it was quite simple to couple the two LSTMs. And also, it's very important, LSTM is very good when you have temporal sequences, because it remembers the information about the error on the previous time step. So it's very suitable for the problem we were going to solve. We try to apply neural assimilation to the problem of predict oxygen diffusion across a blood-brain barrier. So these are the questions. We created our data set. More info, you can find more info in the paper. And we trained the network using the 85% of the data, and we tested the network using the remaining 15% of the data. And this is the loss function. So this is one position, what happened in one position of the blood-brain barrier. You can see that the red line is the neural assimilation, the green one is Kalman filter. So there is a difference, of course, because neural assimilation is just able to emulate an optimal interpolation. Kalman filter is propagating is using the forecasting model in order to update the covariance matrices. So there is a difference, but it's not so big. This is for another position in the blood-brain barrier. If we check the error, so the distance between the Kalman filter and the optimal interpolation, we can see that they are quite close. And the neural assimilation, which is emulating an optimal interpolation, the solutions are quite close. So we are happy with that. This is what happened at different levels of the of the barrier for different positions. And the previous graphs I was showing are just like, say, 2 lines of this 3D plot. If we focus now on the execution times, of course, neural simulation has to be trained, so there is like a back propagation, and it takes time. In fact, we have like, you can see that the training part is quite heavy. But when you have finished to train the network, then you can have the data assimilation in a very, let's say, near to real time. But for us, real time is the execution time, is the time we need to stop and restart the execution of the forecasting model. The Kalman filter is like, say, that the execution time of a Kalman filter is almost, let's say, the same of the training process. What happened? A question could be, what happened if I want to like, in a context of continuous learning, I want to update the neural assimilation? Should I retrain the network? No. There are few approaches in the context of continuous learning to fine-tuning the network. So just adding the new time steps. As a future work, we are going to use neural assimilation in the context of pollutant concentration forecasting in London. And this is a domain we are working on, which is actually where is the Imperial College London in South Kensington. On the bottom, there is the computational fluidodynamic simulation of the pollution propagation in the streets. And forecasting software is named Fluidity, and this is a work in the context of 2 big projects we have at Data Science Institute, which are eNail and the Magic project, Magic 8 project. Work, there are a few questions. The first point would be what the network should look like if we want to emulate a standard Kalman filter, if we want then include the forecasting model, the update of the background error covariance matrix, and etc. And it is quite challenging. We have to change the structure of the network, of course. And what happens if we want to design the network to emulate a variational data assimilation, which is another point that I will be able to work on. Very much for your time. If you have any question, please don't hesitate to send me an email. This is my email address. Thank you again. Bye.
Hello, everybody. This is Vishwas Rao. I would have really liked to give this presentation from Amsterdam, but I'm happy to give it from my home. So today I'll be talking about a machine learning based importance sampling method to compute rare event probabilities. So this work was done with my colleagues at Argonne, Romit Maulik, Emil Constantinescu, and Mihai Anitescu. So the motivation for this work comes from the recent spate of extreme events, extreme weather events, such as flooding, earthquakes, tornadoes, etc. So all these have had a severe impact on both on societal life and also have economic impacts. So many of these events were actually classified as 1 in 100-year event or 1 in 200-year events. But unfortunately, even in the last decade, we have had more than 2 of these events. So it's clearly not as rare as it was classified. Some of the examples are this Hurricane Harvey, which caused basically extreme flooding in parts of Houston in 2017. It severely impacted the day-to-day activities, and there were other infrastructure failures as well, which caused cascading power failures in USA in 2003. 2012 in India, which affected nearly 400 million people. 2012 again in Nova region, which affected several people for more than a week or so. Not only does these events have extreme impact on the lives of the people, they also cost the exchequer quite a bit of money. So just in the last 2-3 years, the amount of cost incurred in US because of these extreme events are upwards of 300 billion. So clearly, it's an important problem to study and understand well, understand the risks, and in some situations also attempt to mitigate these risks. So by understanding the risks, I mean learning how to compute the probabilities of these events. So these are, again, as I alluded to before, are of great importance. So some of the applications where we see such problems are from weather. Examples are hurricanes, tornadoes, flooding, and oceanography. Some of them are what are called as rogue waves. We also see these applications in power grids. So in particularly according to the North American Reliability Corporation, or I don't know what C stands for. I know that NER stands for North American Reliability. So it demands that the number of minutes of power loss for an year should not be greater than few minutes. As in, there should not be a power outage more than 1 or 2 minutes per year. So this translates to a probability of the order of 10⁻⁴ to 10⁻⁵ So these problems are typically formulated as transient security in presence of some uncertain inertia, and they are mathematically formulated as dynamical systems. So I'll just give a brief overview of my brief overview of the challenges involved and some of the results which we obtained in this study. So one of the major challenges with regards to rare events is that there is never enough data that corresponds to the rare events. In some cases, it could be the first data point as well. And most of the times, the models which we have are computationally very expensive to simulate, and just using multiple simulations and using Monte Carlo to estimate the probabilities is probably out of the question. Because, so for example, let's say that we are trying to estimate the odds of an event whose actual probability is in the order of 10⁻⁻3, which is not very unrealistic. And we have a model whose simulation takes about 10 minutes for each simulation. This is again not at all unrealistic. So with such very reasonable criterion, if we are to obtain an estimate that is about 10% accurate, we would need to do about 2 years of serial computation. So clearly, this is not tenable. Hence, we have to look for more advanced methods, techniques to improve the estimation capabilities. So this basically involves characterizing the tails of the distribution. So one of the challenges, other challenges are nonlinearity and non-Gaussianity. So most of the problems which we study which are studied in the literature assume Gaussian distribution and sometimes even linear problems. But that is clearly not the case. We live in a highly nonlinear world, and the uncertainties are not necessarily Gaussian. So these are some of the challenges. And here we can see in some of the plots here, this is the Monte Carlo estimate for a simple problem. It converges rather slowly. And some of the methods developed here, they converge very fast. So on the y-axis, basically the relative errors, and on the x-axis is the number of model evaluation. So some of the features of these methods are about accurate results with about 1,000 model evaluations for small systems. These are extensible to large systems actually. And there are sound theoretical foundations of which are used to develop this method. So in this specific talk, we'll actually build on our previous work and look to use machine learning to alleviate some of the computational burden that was there in the method which we had developed before this work. So let's go through the existing approaches. The current approaches, I mean, Monte Carlo simulation is almost universally known. So the idea here is to, let's say, this red colored or buff colored region is the region of interest, and that's where our rare event lies. And this is the entire probability space, that is the square or the round, sort of the rectangle. So the idea is to just sample from the square and just count the fraction of the samples that actually lie in this region. So that gives an estimate. That gives a that is basically the Monte Carlo estimate. So importance sampling is another technique that was developed in the 1950s. So the idea here is to basically first construct a biasing distribution. So the biasing distribution tries to make use of any knowledge we have about the physical phenomena or any understanding about the uncertainty. Let's say that we understand that the region of interest is within this triangle. In that case, you sample from the triangle, but at the same time, what you do is to reweight according to adjust the weights of the samples so that you make it seem as though it came from this. So it's essentially Monte Carlo, but reweighted according to the biasing distribution. So this is another approach. It's a very commonly used approach. So Monte Carlo, obviously, as I alluded to before, is pretty slow. Importance sampling in higher dimensions could cause some issues as it is. And also it is very difficult to determine the biasing distribution. So other approaches are, so the nested subset methods is another approach that is very commonly used. This was developed in the early 2000s. So the idea here is, instead of directly solving for a problem that is that is rare event, you build up to it, as in you construct smaller thresholds and use conditional probability to eventually arrive at the rare event probability. So this basically requires evaluation of conditional probability, and in some sense it's the constructing of this biasing distribution or evaluating this conditional probability. You cannot do it in parallel. You have to have the previous level before you go to the next level. It's inherently serial. So there are other methods which make use of multi-fidelity and surrogate models. This basically leverage a hierarchy of low-cost models to reduce the cost. So the advantage of this, of course, is that it can be used on top of any method to construct the biasing distribution to reduce the cost. There has been a recent interest in terms of using large deviation principles to evaluate the probabilities. These are, again, pretty effective in some cases, especially when the rate function, underlying rate function, can be derived easily. In such cases, the large deviation principle can be very effective. However, there is one caveat with the large deviation methods. So one of the issues is that if you have these work best when you have certain dominant direction where the tail lies. So if the tail lies in a certain dominant direction, or most of the tail mass lies in a certain dominant direction, then the large deviation principle actually works really well. However, this might not be the case all the time. So we might have a more distributed probability mass. In such cases, large deviations actually fails to capture the tails accurately. So let's look at the problem formulation which we are trying to solve. So we consider dynamical system, x prime is equal to f of x. So with the time range 0 to t, and we have the initial conditions, and the initial conditions is what is uncertain, and x lies in the omega space. We are interested in basically estimating this excursion probability here. So this means that the maximum of consider a trajectory x between 0 and t. We want to estimate the probability that the max of this trajectory multiplied by a certain canonical basis vector c exceeds a value u. That means it basically is telling that certain component, if x is a n-dimensional vector, we are looking at a certain component of x, and we are trying to estimate the probability that this component of x is going to exceed u at some point in the interval 0 to t. And we are also assuming that the initial state of the system has a probability distribution function p. Of course, when f is linear and p is Gaussian, the evolution of x is analytically tractable. So, however, when f is nonlinear, and then the evolution of x is not analytically tractable, that's why we need to develop techniques which can be applicable for such problems as well. Sorry. Yeah. So the idea here is, so consider the subset omega of u, which is a subset of omega, and let that denote all initial conditions. This is of course not this need not be a finite. This is obvious. This set obviously consists of infinite elements. So does omega. So denote the set of all initial conditions that could cause an excursion. That is, let's say x0 belonging to omega of u that cause or x0 that belongs to omega and that caused this excursion. Then probability, we can easily estimate the probability of the excursion by evaluating the measure of omega of u. So this omega, this mu basically represents the probability measure associated with the initial conditions. Finding PT of u basically amounts to finding omega of u. Now, what we do here in this work is basically we will use what is called as Rice's formula to gain insights about omega of u. Of course, for most problems, we can never be able to compute, most problems of practical importance, which we are never able to compute omega of u. Analytically, hence we have to use techniques to gain insights about omega of u. So the overview of approach is our approach basically relies on Rice's formula and excursion probability theory. So what is exactly Rice's formula? So Rice's formula basically tells that the probability of a random process exceeding a threshold u can be approximated by Euler characteristics of that by an Euler characteristics set with a high degree, and also this converges to this converges exponentially quickly as u tends to infinity. That is, for high excursion values, this estimate becomes more and more accurate. So here again, the assumption is that x is a centered unit-variance smooth Gaussian random field, and phi of AU is basically the Euler characteristic of the excursion of this following excursion set. What is an Euler characteristic? To understand Euler characteristic, we can just look at 1D. So basically in 1D, Euler characteristic is basically the number of disjoint intervals in A. That is what is Euler characteristic. So the Rice's formula, which computes the expected number of upcrossings of level U, and Euler characteristics are basically similar, and hence has been used to approximate the excursion probability. So this is the actual relation, but there is the Rice's formula estimates this particular relation here. Okay. The Rice's formula is given by the following expression here. So the intuition behind this is basically it looks at all sample paths that exceed the threshold and have slope between 0 and infinity, between the time 0 and t, and you integrate over it. It's very simple. So here phi t is basically the joint probability distribution of the process and its slope. So basically phi t gives us an indication of how many sample paths with slopes between 0 and infinity cross the threshold u, and you multiply by the expected value, multiply by the slope, and you integrate it and obtain basically the expected value of the upcrossings, number of expected upcrossings. So phi t is, as I mentioned before, is a joint PDF of the process and its derivative. So of course, for a random process, the derivative is in a mean square sense. So what our method uses is the insight that our method uses is that the values of the time t and slope y at which this particular quantity y phi t of u comma y is large contribute most to the integral. So we have to note here that since u is very high, that's the case which we are interested in. In general, this integral is going to be low, and moreover, since this integral is low, there might be very few points actually that contribute to the integral. So we are going to try to gain an insight about those few points and use that to actually compute the integral. So that is what our method uses. So we are going to use the fact that there are few times t and few slopes y for which y phi t is very large, and we'll use that to construct an approximation to omega of u, and then finally estimate the measure of omega of u to basically compute the probability, the excursion probability. Okay. So this is a this diagram basically illustrates our approach. So let's assume that G is a map from RD to R2. RD is basically the state space, and R2 here basically measures the process and its derivative. So X is basically the trajectory. C transpose X is the trajectory of that component of interest, and C transpose X primed is the derivative of the same component. So this is basically defined by the dynamics for a given initial conditions and at a specified time t. And let's say we have some way to evaluate the joint probability density of the process and its derivative and the product. So basically y phi t. So then we look at points, we try to identify points that contribute the most to this particular integral, and then find an inverse mapping in the input space. That the input space is basically the initial conditions. So inverse mapping will be G inverse. Of course, G inverse need not be unique because it's an ill-posed problem. For example, for D greater than 2, there might be multiple initial conditions that map to the same output space. So we try to determine all the input or the initial conditions that map to this particular observations or this particular important observation, and then basically use those initial conditions to develop biasing distribution. This biasing distribution will then be used to estimate the probability. So basically, we'll use a Bayesian approach to estimate. we'll use an Bayesian approach to estimate this the set in the input space that actually map to the observations picked in the output space as denoted here. So let we define xi as the set of all initial conditions in omega that such that g of xi comma ti is the appropriate slope and is equal to the threshold value. So obviously then an approximation of omega u can be constructed as an union of all these initial conditions. So note that this could be infinite in principle. So as we increase the number of n's, or as we increase the number of observations, the omega hat of u approximates omega u better. So obviously, since we are looking to estimate rare events, we might not need that many observations. Hence, we'll discuss more as we go on, but a few observations might suffice. But in principle, this can be infinite, and hence, like omega hat u can probably never be equal to omega of u, but we can construct a decent enough approximation such that the probability estimates are fairly accurate. So to find xi's, an obvious way is to solve an inverse problem. We have to solve an inverse problem. To solve this inverse problem, there are many ways to do it. One of the ways is the Bayesian approach. In the Bayesian approach, of course, we assume, since assuming, let's say that P is Gaussian, we'll discuss a little bit of what to do when P is non-Gaussian. Let's say that when P is Gaussian, then we have a prior probability distribution for the we have a prior probability distribution that is given by the mean and covariance of the initial Gaussian, and to obtain the likelihood we are going to use the observations that are basically drawn as samples from the unnormalized y phi t. So basically, a statistically consistent way of obtaining observations is to draw samples from y phi t. So drawing samples from y phi t would mean that you will end up picking up most samples from high density or from regions where the mass is concentrated. That's a statistically consistent way of getting the observation. So observations will be used as likelihood. And of course, for the G, the forward map G is basically the model. So we have a Bayesian framework. However, we also need the covariance of these observations. So to get the covariance, so we'll talk about the covariance soon. And now, given that we have the posterior and the prior, we have the prior and the likelihood, we can construct the posterior, that is xi given yi, as shown in this equation. And making a Gaussian approximation, we make things become easier. We can write the likelihood or the posterior distribution in a closed form, at least up to a proportionality constant. And now I'll talk a bit about constructing yi from unnormalized y phi t. So we have to determine which slopes and which times are actually important. So this basically requires evaluating y phi t. One obvious way is to just use Markov chain Monte Carlo to sample from y phi t, assuming that we can write down the likelihood of, or the posterior likelihood of the distribution. So I want to emphasize that irrespective of the size of the state space, the y phi t space is always going to be 2. This is because we are just looking at at one component of the state and its derivative. So irrespective of the size of the state, we are always going to have a 2-dimensional PDF. So sampling from it is easier, even using a Markov chain Monte Carlo. Now, of course, to sample from this, we will need to evaluate y phi t. So this is a very important step for this, for our approach. So let's say that when P is linear, when P is Gaussian, this is a typo, it should be Gaussian, and the dynamics is linear. So we can basically write it as shown here, and then the time evolution can be written in closed form this way. I'm going to discuss a little bit about how to deal with nonlinear and non-Gaussian. And then when x0 is normally distributed, we can write x of t as a Gaussian process. So the Gaussian process has the following x hat and covariance as the mean and covariances as given here. So we have a nice closed form, and we can also evaluate the joint PDF of the process and its derivative. So this formula is available in Rasmussen and Williams, the Gaussian processes book. And although this formula looks fairly ugly, but I mean, one can easily evaluate this and it's tractable. So now the concern is that generally it might not be linear. And so let's say if it was linear, in case of linear, we could actually directly use the Rice's formula to obtain an estimate. And that is fairly accurate. That gives very accurate estimates, and we have tested that. But we are going to solve this problem for a nonlinear and potentially non-Gaussian. So when the dynamics is nonlinear, then what we do is we basically use the we use the mean of the initial distribution and linearize around the mean and use that as a proxy to evaluate y phi t. And then again, we'll use this y phi t only to draw samples and find the regions in the input space that potentially cause excursion, and again correct this error by using importance sampling. However, when we have non-Gaussian distribution, or when the initial conditions is distributed in a non-Gaussian manner, then we cannot evaluate y phi t even by linearizing. In such cases, we have to resort to some sort of approximations, such as using Gaussian mixtures to represent the initial distribution of the state space. That's what we do. So now, to sample from y phi t, what we do is we basically use the Markov chain Monte Carlo. So on the left, we see the figure, the product of the derivative and joint PDF of the state and its derivative for u is equal to 17, that is the threshold. And these are samples drawn using Markov chain Monte Carlo. We specifically use delayed rejection adaptive metropolis algorithm. And these samples basically will be used to construct the likelihood of our Bayesian inverse problem. Also, one thing to note is that because we need independent samples, what one could potentially do is to look at the autocorrelation between the samples, and we see that for about 10, the autocorrelation dies down to 0, and we can, if you pick every 10th sample in the chain, you will sort of ensure independence heuristically. That's the idea here. Of course, I already spoke about the need for mean and covariance for the likelihood to construct a consistent Bayesian inverse problem. So we look at basically yi, ui at given ti. That's what we look at. So if you look at for u is these are basically the same sample, same coordinates, the time comma slope coordinates. For the same time comma slope coordinates, we see that for u is equal to 14, it's at the sort of the tail of that Gaussian, and for u is equal to 17, it's at the center, and for u is equal to 20, it's at the tail. So basically, the covariance here means that it will also pick up initial conditions that map to values higher than 17. Sometimes it might also pick up initial conditions that map to values lower than 17, but that is okay. We are going to anyway use importance sampling to correct it. But the good thing is that it also picks up values that are greater than 17. So it's not just the just the values that map exactly to 17, because we are clearly looking at excursion probabilities. So hence we also need initial conditions that map to values higher than the threshold in the omega of u, in the approximation to omega of u. So we will actually use Laplace approximation to estimate this mean and covariance. Okay. So now there are many ways to solve the Bayesian inverse problem. We can just use the map-based or find the map point and then find the covariance of the solution. Find the covariance of the posterior by just estimating the Hessian at the map. So this is what we do in our paper. This is on arXiv. I encourage you to look at the paper. So we basically solve the inverse problem using the negative log likelihood as a cost function and use the Hessian inverse at the map point to approximate the covariance of the posterior. Basically, we use the LBFGS to solve the optimization problems, and we use the adjoints to obtain the gradient. Now, in the MCMC-based importance sampling, what we do is we directly sample from the posterior. This is basically using DRAM algorithm, sample from the posterior. This is different. Note that this is a different stage. So we already used MCMC to sample from YFT. This MCMC is different. This actually samples from the posterior distribution. So in this, however, we try to avoid solving this Bayesian inverse problem, and instead we try to find an inverse map using machine learning based approach. So the idea here is that instead of solving multiple Bayesian inverse problem, what we do is we sample from YFT and try to find an inverse map to the input space. So basically, the inverse map by solving an Bayesian inverse problem might be expensive to obtain. So the idea is that so what we look is, can we build some data-driven surrogates for approximating the pre-images? That is, so we want to find a map from R2 to R using surrogates. RD to R2 is a forward problem. R2 to RD is the inverse problem. So we are going to use a fully connected neural network to approximate this map. So to train our network, what we do is we use multiple examples of forward simulations. So the good thing is that here one simulation gives us nearly 50 training data sets, because we are looking at different values of time, and we don't have, so one forward simulation gives us multiple data set to train. That is the good thing about this process. So basically, our neural network training is a non-convex optimization, and we use the standard ADAM stochastic gradient optimizer with a learning rate of 0.01. Consistently reducing accuracy on a held out data set is used to terminate the optimization, that is to prevent the overfitting. Now, how do we quantify the ability? We track the reducing objective function and we stop it when we see there is no improvement. Whatever the validation data set is used is to select the best model. So basically, the scatter plots on the test data show that it's a good fit. The true and predicted map well. So it's a nice R-square fit. So all the training is very great. Now let's see how this actually works on the problem. So now we use this machine learning map, which maps the R2 to RD to construct our biasing distribution, importance biasing distribution. So these two actually were, as I mentioned earlier, were done in our previous work, which we have submitted to ScienceJUQ, and it's also available on the arXiv. So here what we did was we basically draw samples from the posterior, and we have to do it for multiple observations. And then we'll use this samples to basically construct empirical mean and empirical covariance. We can also, if we have to appropriately weigh different observations, then we actually fit a GMM instead of using just one Gaussian mixture model instead of just using one Gaussian. And the weights will be according to how important they are in the integral. That is basically how high this YFT is for that particular observation. For a map-based IS, what we do is we just get an approximate distribution by solving and then using the Hessian inverse to approximate the covariance. Again, we can use multiple, if we use multiple observations, we could easily use Gaussian mixtures and with weights proportional to the importance of the observations YFT distribution. Here, for the ML-based IS, however, we don't solve any inverse problem. But what we do is first we sample YFT. This is very easy. This is just sampling from a two-dimensional space, whereas this will require sampling from d-dimensional space. So we sample from a two-dimensional space. We collect a lot of samples, and then we just use the ML-based inverse map, which we constructed here to approximate the inverse solution. So now this inverse map, one sample here gives one inverse map based on this ML-based solution, and then we can construct a Gaussian mixture or a Gaussian approximation to as our biasing distribution. Note here that one solution might yield multiple maps. Here one sample gives map, so we can sample more. This I again want to emphasize that this sampling is easier, whereas this sampling is harder because you're sampling from a d-dimensional space. Okay. Now that we have the biasing distribution, we can use the importance sampling to estimate the probability, excursion probability. So now we are ready to test this on a Lotka-Volterra example. This is basically a prey-predator problem which denotes the evolution of the population of prey and predator. So we are interested in estimating x2 exceeding 17. x2 is basically predator population, I think, prey population, I think. So now this figure shows the nominal and biasing distribution. So the nominal distribution is as shown here. This it has a mean 10, 10, and covariance of 0.8 with identity. So this is the nominal, the blue color, and the orange color basically denotes the biasing distribution obtained by solving this lengthy procedure, which involves solving Bayesian inverse sampling and Bayesian inverse problem and machine learning. So we clearly see that our biasing distribution actually picks up from the tails of the nominal distribution, and now we'll use this to see how well we do. So basically, this first line, with I think it is probably cyan to green color, cyan plus green by 2 probably. This represents the Monte Carlo estimate. The blue line basically represents the machine learning based importance sampling with just 1,000 training data points. That means you just use 20 model runs and you get about 1,000 training data points, and you train it and find the inverse maps and use that to construct the importance sampling, and then do the importance sampling to get the probability estimate. So we see that it doesn't give that great results. It's okay. I mean, it's possible, but still doesn't show any decrease. When we use 5,000 data training points, that is the red line, we see that it performs slightly better, but again it doesn't inspire much of a confidence. As we increase the number of model evaluations towards the end, it is sort of raising. The probability estimate is the error is raising. Then we do it with 10K training points. This is much better than the first two. Obviously, we have more training points, but again, this is still not acceptable. But the one with 20K training points is a very acceptable result. It's about 1%, less than 1%, or less than 0.5% error for about 10,000 model evaluations. So in addition to 10,000 model evaluations, we also have to include the computational cost of the training. So approximately to generate 20K training data points, it requires about 400 model evaluations. As I said, each model evaluations gives us 50 training data points, and training the data set required about 180 seconds. This is basically a desktop with Python 3.6.8. Also now the inference cost. By inference cost, I mean using the trained data set to estimate the inverse map. That is almost negligible. It's about 2 seconds for 2 seconds for about 10 power 4 evaluation, 10 power 4 model, 10 power 4 samples. So overall, I think it's the training and the inference costs are negligible, and if you just use the model evaluations, we see that it beats the Monte Carlo by about at least about the accuracy is about I would say 3 to 4 orders of magnitude. Well, at least 3, if not 3 orders of magnitude for the same effort. So this is very encouraging. Now we also solved larger problem, a Lorenz 96 system with 100 dimensions using map-based and MCMC-based IS. But for this paper, we did not do the Lorenz problem with machine learning, but that would be an interesting test case because you are trying to map from 2 dimensions to 100. Probably we'll have to use advanced machine learning algorithms to do that because the mapping, you're mapping from a low dimension to high dimensional space. So in that case, we might end up requiring more training data points, but still I think it is doable. So with that, I'll leave you with some concluding remarks. So in this paper, we have basically presented an CMC and ML-based importance sampling algorithm to estimate the probability of extreme events. This method basically comfortably outperforms MCS. So another interesting thing is some parts of this method can be parallelized. We are currently working on some theoretical support for this method. We also have some extensions to multiple variables, as in we already submitted the paper with 100 dimensions. So this algorithm can be extended to problems beyond dynamical systems. We will look at, we'll examine closely at larger problems and also look at non-Gaussian and nonlinear cases more which have a high degree of nonlinearity and non-Gaussianity. So the references to this work are available on arXiv. So we already received the reviews for this paper, and I'm addressing reviewer comments. Hopefully soon it will be published. So both the papers are on arXiv. I encourage you to look at. And if you have any questions, please feel free to write to me at this email ID. With that, I'm going to stop.
Good morning, everybody. I'm Nachiketa Chakraborty from the Data Assimilation Research Center at the University of Reading. And thank you for joining me at whatever time you're joining me to listen in to this presentation. And thank you to the organizers for being able to facilitate this option of uploading the slides. I wish to present a work that I've done in collaboration with Peter Jan van Leeuwen, Manuel Pulido, and Michael Decquera on developing a Bayesian inference framework for causality. This is a framework which we seek to apply to oceanography, and I will talk more about the mathematical methods though in this talk. Here's the little outline. I will first motivate our approach whilst listing the limitations of the current methods and current approaches. I will then talk about building the framework from scratch and talk about the conceptual and mathematical challenges, and then finish off with the connection to data assimilation and give an example with the toy model. So causality is an age-old pursuit across disciplines ranging from sciences to social sciences. So here we see causality study on understanding relationships between neural spike trains. This is an example of stock networks and understanding the relationships between different components of this network. Here's an example from the physical sciences where we want to where the authors want to understand the relationship between the flows in a turbulent liquid, and this is actually very relevant for our application in oceanography. So we, in fact, wish to study the global oceanic circulation. That is the ultimate problem to which we want to apply our methods. Specifically, we want to understand the relationship between the large-scale flows between the Indian, South Atlantic, and South Ocean, and the small-scale turbulent eddies south of Africa, as shown in these in this figure here. Now, despite a long history of study of this discipline of causality, it's rife with open challenges, and I will especially highlight some of the mathematical and conceptual challenges. But for that, we need to understand what does causal inference or discovery entail. Causal inference entails, at its very core, certainly in the physical sciences, a couple of aspects. First is the arrow of time. It is this idea that causes precede effects, as is astutely noted by this bright young man who's telling his parents how he's supposed to think about consequences before they happen, which is exactly what is the case. In addition to this time lag between causes and effects, we also need to have a mechanism with predictive power. In other words, if X and Y are causally related, if X has predictive power on Y and vice versa. And the whole business of causality is to take these two and quantify it. And that is what we will rely on. Now, the current approaches, the current methods have certain limitations, which prompts us to look beyond them or extend them. The complex interplay between driving and driven processes in nonlinear systems, such as in the interocean exchange problem that we wish to solve, that requires us to have very sophisticated tools. And the current methodologies are limited mainly in the following two ways. First, we have a very good understanding of large-scale linear interactions. However, a much poorer understanding of nonlinear causal interactions, which are perhaps operating on smaller scales. In particular, a thing that is not addressed pretty much in any approach are joint causal relationships, which means that if you have a bunch of variables X, Y, and Z, and as in this model, which is the Lorenz 63 model, which is very straightforward and yet a very powerful model for the atmosphere and other systems. So in this case, you see that there are three variables X, Y, and Z, and the rate of change of Y and the rate of change of Z both have terms which are product terms. So X and Z jointly influence Y, and X and Y jointly influence Z, as is shown in this little picture from our paper, which is in preparation. And this is what I mean by joint causal relations, where X and Y jointly influence Z. And this type of an interaction is very hard to quantify and identify with the standard approaches in causality. The other limitation is all approaches, pretty much bar none, have very poor uncertainty estimations. And the main reason for that is there are multiple sources of uncertainty. So while there may be ways of quantifying the measurement uncertainties on the variables that are observed, there are uncertainties in estimating the causal relationships. There's also uncertainty related to the selection of the different variables which are causally relevant. And these are typically not factored in, and we seek to factor all this in our approach. Now, in order to get started, we first need to understand, or the very first thing to study causality in complex nonlinear systems is to look at a measure which will quantify the strength of causal relationships between different variables, between different processes. And there is a whole gamut of gamut of options that are available that have been used with some degree of success. Granger causality being the first and foremost of them, which essentially lays down the framework of studying causal relationships in terms of conditional dependencies and independencies between variables. So it's a probabilistic framework, and actually a lot of the other measures are derived based on Granger causality. Interventional probabilities is used for systems where interventional systems, in other words, systems where you actually affect a change and then look at its effect. And this is quantified in terms of the do calculus that Judea Pearl built, who's of course a huge name in causality and has done a lot of fundamental work. And then there are many information theoretic measures such as transfer entropy, directed information transfer, conditional mutual information, and so on. And last but not least, correlations. Correlations are, of course, still very powerful and relevant, but are linear in nature. Now, from amongst this, we pick conditional mutual information for the reasons that A, it's sensitive to nonlinearities, unlike partial correlations. It has an analytical limit in the case of two Gaussian processes whose relationship you're trying to compute. And this is very rare. There's not too many analytical results that are available to benchmark any methods. So this is why conditional mutual information is very useful. And also there are lots of computational tools, such as the one developed in Kraskov and the improvement in Pete and so on. So there's tested tools which seem to do a good job. And that's why we pick conditional mutual information as the measure. But then what is the definition of conditional mutual information or mutual information in general? Well, essentially, if H is the Shannon entropy of a process or a random variable X, then the mutual information between variables X and Y is the reduction in the entropy of X given measurements of Y. So in other words, if entropy represents the uncertainty in a variable, then the reduction in entropy in one variable on account of information on another variable is the mutual information. And you can see why this essentially implies a conditional dependence. Because if you reduce the uncertainty on one variable by information on another, then surely they must be interdependent. And this is also expressed in terms of the probability distributions of the two variables and so on. Of course, there's multiple variables. You extend it by conditioning on different variables, and this is the conditional mutual information indicated here by CMI. Now, we define the causality strength as conditional mutual information or mutual information divided by the conditional entropy in presence of all the causes, which essentially represents the fractional contribution to the total influence of every process on X. And this is a very intuitive definition and a very useful normalization, where, of course, the conditional entropy is actually the sum total of all the different mutual information components and indeed the uncertainty in the variable itself. Now, as we know more about causal processes, as we know and have measurements on different processes, this conditional entropy goes up, and the fraction hx by hx given all causes goes down, and that basically means that we have a better understanding of the relationships between or of the variables that drive x, the target variable x. And ultimately, we want to describe them via probability distribution functions as a way of quantifying the uncertainty on them. And this is naturally done in a Bayesian approach. So let's look at these two limitations in more detail, which will help us to build the framework. The first is, of course, this idea of linearity and using correlation measures. Now, here's a little cartoon which shows what most of us are actually guilty of doing, which is when we try and find a relationship between two variables, we try and do all sorts of things to fit curves essentially and do them in sophisticated ways like compute the confidence intervals and we use different functions and so on. Now, of course, correlations are tricky, and then as the classic saying goes, correlation doesn't imply causation. And also a lot of these correlations and regression measures are ultimately assuming a certain linearity. And we'll see how this creates problems in even very simple models, such as this one. So here, we examine the relationship between two variables, x and y, which are two time series, which is the sort of variables we'll deal with in our problem. And these are very simple. This is a very simple example where the two time series are essentially oscillatory functions, as shown in the equation to the bottom. They're product of sinusoids. And this is a rather simple mathematical model, but this is actually a pretty good description of certain astronomical systems and their variability. So it's actually quite a useful and insightful model. Now we take a very simple case where we have just one sinusoid in both sinusoidal component in both x and y, and they have and x and y have a lag between them. And of course, the study of lags is very important because we in the context of causality, because obviously we want to know which process and which variable comes before the other to identify the cause and the effect, but also the physics of the system, so to speak, is sort of built into what is the value of the lag, and in this case we have a straightforward lag of around 150. Now the relationship between y and x, which is also known as the phase diagram in dynamical systems or in physics, is not linear. So so basically you are not dealing with a system where the two variables you're trying to study the interdependence to is not linear. It's this elliptical function, as you would imagine, with the phase shifted time series. And in order to quantify the lags, what is often done is apply cross-correlation functions, as is shown on the bottom left. And so you cross-correlate between x and a shifted version of y, which then identifies the lags as the lag as the one in which most power resides, most of the signal resides. And you can see clearly here, even for such a simple system, while there's a peak at around minus 150, it's not a clear identification of this value. And secondly, there's a trough at around 300 or so, and that's 350 actually, and that is the second lag term, which is not at all clearly identified in this discrete correlation function. What happens if you take the mutual information of these two variables, xt and xt plus tau, where tau is the lag, of course? You see a sharp identification of the lags, both the primary lag and the lag as a result of superposition of the two sinusoids. So when you multiply the two signals, you can see that there's going to be two terms when you expand the product of signs. And the mutual information function identifies this sharply because it's a nonlinear measure. So essentially, you want to have a measure that is fundamentally sensitive to nonlinear relationships, and that's why mutual information function is actually a good measure. Now, the second issue that we spoke of are the sources of uncertainty and then indeed bias. And there are multiple sources of uncertainty and bias, but we will focus on the estimation uncertainty, which is actually very relevant and yet not always factored in. Now, the causality estimator is essentially a function of the mutual information, as we said, and we have very few analytical or theoretical limits to benchmark our results, but we do have the mutual information for two Gaussian random variables with covariance rho being 1/2 log of 1 minus rho squared, as is given in the bottom. So this is an analytical result, and then of course we'll generate data with these two Gaussians and estimate it and compare with this analytical result. Now, and in doing so, we want to test if there is an uncertainty or a bias in the estimation method. The method that we use is this method developed by Kraskov and collaborators back in 2004, 2005. And essentially, the method comprises of using a nearest neighbors algorithm. So we basically generate multiple realizations with these two Gaussians with covariance rho. We apply the Kraskov method and test the k dependence as a source of the uncertainty. And as you can see in the figure here, we did a bunch of realizations for different values of neighbors, from 1 to 2 to 3 and so on up to 10. And we histogram the values of the mutual information that we get, and we compare these results, these estimates, with the analytical estimate, which is in red. So if you squint really hard, you should be able to see the red dashed line on these histograms. I apologize for the colors. And we fit the histograms with the Gaussian, and the mean of the Gaussian is shown in black, in the black dashed line. And as I said, if you squint really hard, you will be able to see that, firstly, you'll be able to see that there is a difference in the width of the distributions. So sigma, the standard deviation changes. It basically decreases until as the number of nearest neighbors increase to 10. But what also happens is that the separation between the analytical result and the mean estimate, so red and black, also changes with k, and it decreases until 3 and then goes back up again. So it turns out that 3 seems to be the optimal value, where there's a trade-off between the uncertainty and the bias, which is optimal for an estimate. But the most important thing is that there is an uncertainty and there is a bias, and this gets folded in to our prior PDF in our Bayesian approach. So we apply, we basically can apply these simulations in order to inform our prior. Now, armed with a nonlinear measure, a powerful nonlinear measure, and a way to quantify different types of uncertainties, we then set out to build our Bayesian framework. So once again, we have the causal strength defined in terms of the fraction of the total influence of any cause or driving process Y on target process X, and this estimates, each of these estimates are of course based on finite length time series, and therefore we fold in the measurement errors, the estimation errors into the prior, and then compute. Essentially, we compute the causality with Bayes' theorem. So the estimated or observed causality strength is, of course, the true causality strength plus an uncertainty term, and the true causality strengths are what we're after, and then with as we have observations, we can improve on our estimates. Now there's two types of observations, two types of scenarios. One where you have more data with the same variables with the same time series, and then we just use Bayes' theorem and update our existing knowledge. Update the existing values of CS, and then we can use this to compute the full distribution of this variable CS. Now, however, there is the possibility that there is new processes, new variables which come into the picture, and that actually leads to one of our first mathematical challenges in the framework. So let's look at this in more details with an example. So let's assume that we have a process which is not a Markovian process, and so we have just actually one random variable and at different time steps, and the current time step n depends upon the previous time steps as a function of xn, as a function of as the function f, and of course there's the uncertainty term. Now if this is the scenario where we try and understand what is the dependency of the current value of the variable x, and how does it depend on the previous values, this causal connection is defined in terms of the mutual information between xn and xn minus 1, or in fact, even further back in time. Now, if new intuition or theory suggests that there is an additional process y, which is also of interest, then this equation, the above equation, is modified, and the actual dependency is a function f of xn minus 1 and g of xn of yn minus 1. And then we have two causal links, which are basically the conditional mutual informations with respect to yn minus 1 and xn minus 1. So essentially, if you try and look at the different parts of the Bayes theorem, the prior is essentially one-dimensional because we thought that xn only depends upon the past of x, xn minus 1. But the likelihood, as a result of new measurements, show that there are two variables, and xn depends upon both the history of xn of x and of y. And so there is a dimensional mismatch. There's an increase in the dimensionality of the probability space, of the causality space. And this is actually non-trivial. This appears as if it's just a question of knowing the variables, but it is slightly non-trivial in that we can't simply use Bayes theorem, and we need to have we need to fix the dimensionality. And we do. We actually solve this dimensional increase problem by asserting that all the causally relevant processes of variables, they already exist. It's just that we haven't measured every influence, meaning that we don't have observations on each of these variables, but we already know of them. And this is actually a non-trivial assumption or assertion, because what it is suggesting is that we have a qualitative intuition which allows us to take a complete set of causal variables to begin with, and then determine the relationships quantitatively as measurements come in. But once we do that, we fix the dimensionality problem, because we always start with the dimensionality of the number of variables. Now, this can be visualized easily in the graphical form, as you can imagine, where you have a collection of nodes, and these nodes represent these random processes of variables, and the links contain the causality strengths. Now, so we treat CS as a random variable, as you may have noticed. Now, this includes the joint influence of multiple processes, which is one of the limitations of earlier methods that we do that I spoke of, meaning that you can have a situation where Y directly influences X and Z directly influences X, but also Y and Z, as in the Lorenz 63 model, jointly influences X, and we compute terms which reflect this. And so this shows that we also need to have improved graphical methods. So standard graphical methods, which comprises of nodes and arrows connecting the nodes, are not good enough because they don't take into account these end links or these joint influences. Once we have this sort of a picture, then we can use the Bayesian inference method to compute the relationships between these links. And in order to do this computation, in order to have a mathematical basis, we explored various approaches, because there's actually a wealth of literature on graphical methods applied to causality and so on. But as I said, we had to also improve the graphical methods in order to account for these joint influences. So we needed a very general method which would be applicable for all these scenarios as well, and not the standard computations done with graphical methods. Heckerman in this note and in subsequent papers actually shows the formal way, shows the mathematical way. This is this is the paper on structure learning, where you basically have the standard Bayesian inference, but it is split in two parts, where you have a model, which is the network structure or the collection of nodes, M, and you have the links, which are like the parameters of the model, in our case, the causality strengths. Now, the standard Bayes theorem, which we saw earlier, is expanded, wherein the posterior is actually PCS given the observations, given the model or the collection of nodes or the structure. And then there is an additional Bayes theorem on the structure itself, which is shown in these small fonts, where PM, given the observations, is PM, the priors on the structure itself, multiplied by the likelihood function, the likelihood of the observations given the structure. Now note that the parameter learning, so to speak, with this Bayesian inference, with the Bayes theorem, is actually on a continuous variable CS, whereas the model itself, or the structure learning part, is on a discrete system. So, and that's essentially because the collection of nodes leads to a finite number of specific configurations. So that's a discrete system, whereas the causality variable is a continuous variable. So once we have this set of 2 or 3 equations, this is very powerful, because this allows us to then go to where we want. If we now use our assertion that all the causally relevant nodes and variables are already present, then M is fixed, and the M dependency drops out, and the Bayes theorem on the discrete Bayes theorem on the models, that becomes absolutely trivial. And we are back to the usual Bayes theorem, which is learning the parameters or the causal links of this graphical model. So we're back to the usual way, in a sense, of doing things, but only after having made these assertions on the base of a very robust mathematical model of structure learning. Now, where does data assimilation come in? Well, this Bayesian inference framework that we've been trying to build is essentially naturally naturally absorbed in data assimilation. Data assimilation is the obvious way to go, because remember, data assimilation combines models and observations in a Bayesian way to optimally to provide a better estimate of the state of the system via state variables. The thing that we do here, once we get to this point, which is the top equation, we basically take the state variables as CS instead of the variables, the original state variables themselves. So instead of X being the state variables, CS of X is CS of XYZ are the state variables. And so in this case, then, CS, which contains all terms representing all true causal relationships, which include the direct links as well as the joint influences, is like a feature space, and we're learning this feature space with Bayes theorem. And when we do this in an iterative manner, we basically have what is essentially a data assimilation approach, where we have a prior set of state variables, CS of X, which could be based on numerical models or analytical toy models. And then we have a bunch of, well, actual observations, which are, of course, then translated into the observed CS values. So there's an estimation step, as you see in this bottom part of this flowchart. And that is that leads to the data, and then we assimilate, and in effect, this is this equation here represents a single step of this assimilation process, which leads to the posterior. And of course, we do this over and over again as new data comes in and as new intuition comes in. And our framework is powerful because it allows us to add more variables and still not have to recompute everything from scratch. So this is the power of the method. Now I come to a little example, a toy model, which is a rather simple toy model. It's a linear system where Z and Y are simply noise, but they drive X in the form of this linear superposition. And again, we assume, or we have the situation where we think that Y is the only driving process, and we don't know much about Z, in which case there's a flat prior on Z, on the causal relationship between X and Z. And once we have the observations, which are, of course, in this case, mock observations generated from those noise terms, then we compute the likelihood and use Bayes' theorem to compute the posterior. And this is a little blow up of the region where the most of the signal rise. And this basically shows that because we have a flat prior, because we have a high degree of uncertainty and, well, a high degree of prior uncertainty on Z and its influence, it's completely driven by the observations. The final result is completely driven by the observations, so the likelihood and posterior look quite similar. Now we want to extend this to our tests to obviously to the more interesting nonlinear systems such as Lorenz 63 and so on. But at the moment, what we've done is we've built a framework which inherently treats nonlinearities because we use a nonlinear measure in mutual information. We factor in multiple sources of uncertainty and fold it into the prior in the Bayesian framework, and the graphical approach allows us to compute joint causal relationships as well. So we expanded the type of graphs that we use, and as I said, the framework is quite powerful because it can take in multiple variables, additional variables, and still not have to compute from scratch. So we want to apply to nonlinear models and then apply to real data so that we can solve the problem at hand. So what are the main conclusions that we have? Well, the main conclusions are that in order to study causal relationships in complex nonlinear systems, we need to have appropriate nonlinear measures which include these joint relationships, these relationships which are of the form XY and YZ and so on. We also need to quantify the uncertainties, and a natural way to do this is in a Bayesian inference framework. A Bayesian inference framework needs to be developed in a careful manner, as we've done in order to apply it appropriately. And the data assimilation framework provides a natural option for this. This framework is applicable to discrete, continuous, and mixed systems. And finally, when we do this data assimilation style causal inference by taking the causal strengths as the state variables, then we can actually determine relationships in complex systems in an iterative way as more and more observations come in. And with that, I'll leave you with my email. And if there are any questions, please feel free to email me and let me know if there is anything else that you would like to know. So thank you very much for joining.
Good day all. My research presentation at the 20th International Conference on Computational Science is titled Node Classification in Complex Social Graphs via Knowledge Graph Embeddings and Convolutional Neural Network. I am Bonaventure Moloko, a doctoral research student at the School of Computer Science, University of Windsor, Ontario, Canada. To begin with, the real world is comprised of several systems and ecosystems, and interactions in the form of relationships is a natural characteristic of any given system or ecosystem. Therefore, interactions between constituent entities in a given system or ecosystem is essential for its sustenance. With respect to the recent advances in artificial intelligence, we can effectively model these complex systems or ecosystems as social networks and analyze them using appropriate artificial intelligence tools and techniques. However, there lies inherent problems with applying machine learning or deep learning models to social network structures. And these problems are, firstly, social graphs can be very large network structures comprising very many social actors. Secondly, social networks possess very complex connections and links between social actors, which can even span to multi-layer social network structures. Thirdly, the physical structure of a social graph is not static. It is naturally dynamic, such that there may exist several structural differences with respect to n-unit progressions over time t. Now that we have some background knowledge regarding the challenges artificial intelligence researchers face with respect to analyzing and resolving problems in social network structures, let us progress by making use of a simple social network structure as depicted by the graph figure on screen, so as to aid in the explanation of the problem we intend to solve in social network analysis using an inductive learning strategy via deep learning approach. To start with, in social network analysis, or SNA, the classification of nodes induces the formation of clusters. Consequently, clusters give rise to homophily in social networks. Homophily, in very simple terms, refers to the concept that birds of a feather flock together. In other words, homophily in social networks foster grouping of actors or individuals possessing similar social characteristics. Furthermore, assuming we have a social network structure as represented by the graph on screen, where the black nodes denote labeled actors and a white node denotes an unlabeled actor in the social graph or social network. Classes or groups of actors are denoted by the dotted orange boundary lines, and relationship between actors or nodes are represented by the black colored lines, which can either be a unidirectional or a bidirectional relationship, depending on the arrow points. Therefore, there arises the problem: how can we effectively and efficiently label these white actors or nodes to their respective classes or groups with a high degree of truth using the existent relationship structure or dynamics of the given social network structure at time t? This open research problem is termed node classification in social networks or social graphs, and our proposition herein aims at solving this open research problem. Consequently, a social network, Sn, can be defined via a tuple comprising a set of actors or vertices, V, a set of ties or edges, E, a metadata function, Fv, which extends the definition of the set of actors or vertices, such as mapping the actors to their respective classes, and a metadata function, Fe, which extends the definition of the set of ties or edges, such as mapping ties to their different relationship types. Therefore, a node classification model aims at training a predictive function, F, such that it learns to predict the labels Y for all actors or vertices V in a social network, Sn, using the knowledge exploited and harnessed from inductive learning over the partially labeled actors or vertices of the social network structure. In this regard, we have proposed a hybrid deep learning model tagged RealVec, which is an acronym for representation learning via knowledge graph embeddings and convnets. RealVec is trained via semi-supervised training, and it employs an iterative learning approach over social graphs for solving node classification problems in social network analysis. Our proposition is comprised of two distinct feature learning or representation learning layers and one classification layer. The representation learning layers are trained by means of unsupervised learning. These layers are essentially feature extraction or dimensionality reduction layers, where underlying knowledge and variable facts are automatically extracted from the social network structure. The classification layer succeeds the representation learning layers of RealVec, and it is trained by means of supervised learning. The classifier is based on a neural network architecture assembled using multiple and deep layers of stacked perceptrons. Essentially, every input social graph dataset to our proposed model undergoes a sequence of data preprocessing, which involves remodeling the social graph to a knowledge graph, as well as transcoding the raw data entities to discrete representations, after which they are normalized to their respective continuous data representations prior to training and testing. Formally, the knowledge graph vector embedding layer is responsible for projecting the feature representation of a given social graph to a Q-dimensional real number space. This is done by associating a real number vector to every unique actor or node in the social network, such that the cosine distance of any given tie or edge would capture a significant degree of correlation between the two associated actors that make up the tie or edge. Furthermore, the convnet layer, which feeds on the vector embedding layer, is responsible for further extraction of apparent features or representations from the social graph via a series of one-dimensional convolution-based operations. Finally, the pooled feature maps generated by the convnet layer contain low-level representations extracted from the constituent actors of the social network. Therefore, the MLP classification layer uses these extracted low-level representations for training a MLP classifier function via mapping them to their corresponding output labels in the Y domain. Hence, these XY pairs are used to supervise the training of the classifier such that it can effectively and efficiently learn how to classify actors within a given social network structure. The algorithm proposed herein for training our hybrid model uses an edge sampling strategy. Hence, at the preprocessing phase, we sample the training ties or edges to be used for training our model. The training ties or edges are made up of actors or vertices that are present in the labeled set of actors. Also, we sample the testing ties or edges to be used for testing and validating our model. The testing ties or edges are constituted of actors or vertices which are present in the unlabeled set of actors. Thereafter, we construct and instantiate our model as required and feed the training ties to the representation learning kernel or core, starting with the vector embedding layer, then to the convolution operations layer, after which the pooled feature maps are used to supervise the training of the MLP classifier function. Our algorithm 1 on screen and detailed in our research paper illustrates the deep learning training strategy employed herein by Rivek. In our research work, comparative analysis was performed using our proposition Rivek against 5 popular node classification models. Hence, the baselines evaluated herein were graph convolutional networks, also known as GCN, large-scale information network embedding, also known as LINE, structural deep network embedding, also known as SDNE, node-to-vec, and deep work models. We experimented over 6 public benchmark datasets, namely Coral citation datasets, CiteSeer citation datasets, Facebook page-to-page web graph, PubMed diabetes datasets, Internet industry partnerships datasets, and terrorist relations datasets. The horizontal components of the tabular results displayed on screen represent the baselines we have employed herein for comparative analysis, while the vertical components represent the average scores of the associated objective functions evaluated herein per benchmark datasets. Thus, for each class per dataset, we have laid emphasis on the F1 score, denoted as F1, and the area under the receiver operating characteristic curve, denoted as RO. The respective computation values for F1 and RO lie within the boundaries of 0 and 1. The F1 scores and the RO scores attain their worst and best values at 0 and 1, respectively. Also, we have highlighted the benchmark model that performed best for each classification task using a bold font with respect to its associated F1 and RO scores per classification task. Detailed results of our experiments, comparative analysis, and further discussions are documented in our research paper. Overall, the remarkable performance of our proposition, Rivek, is attributable to 2 main factors, which are, firstly, the biform nature of its representation learning kernel or core, and secondly, the high-quality data pre-processing techniques employed herein with respect to each benchmark dataset. In conclusion, details of the network pruning, regularization parameters, and other hyperparameter settings implemented with respect to our proposed methodology for Rivek are detailed in our research paper. On screen is displayed a list of our references, a selected list of our references to be precise. And finally, thank you all for your time and attention. Questions and suggestions can reach me via my email address.
Good morning, et al. I am Pasquale De Luca from University of Salerno. I will present our work titled Accelerated Gaussian Convolution in a Data Assimilation Scenario. This work is joined with Professors Delio Galletti, Giulio Giunta, and Olivia Marcellino from University of Naples Partenope. Now we start a brief introducing about machine learning, because machine learning algorithms try to provide an adequate forecast for predicting and understanding a multitude of phenomena. However, due to chaotic nature of real system, it is very difficult to predict data. A small perturbation from initial state can generate serious error. Data assimilation is used to estimate best initial state of a system in order to predict actually and carefully the future states. Therefore, an accurate and fast data assimilation is a fundamental step. Fundamental kernel can be considered a fundamental process of a full machine learning process. Here we deal to introduce a Gaussian convolution operation, which is a central step of data assimilation approach, and in general, in several data analysis procedures. Now we see a brief outline that describes how the presentation is organized. We see in the first section a mathematical background, which contains several numerical procedures. After we see in the second section the parallel approach related to our main contribution with the subsection. And with the second last section, the experimental results confirm our main contribution. At the end, we see the conclusion. In this work, we consider the three-dimensional variational problem that are considered to minimize J, which depends in this context by the penalty and quadratic data fidelity theorems. J is the objective function to minimize. In this context, we do this assumption with background and observation error with related covariance matrices. The three-dimensional variational problem can be linearized by minimizing J tilde, where H is the first approximation of a Jacobi matrix, D is called the misfit terms, and V, variable V, introduce and denotes the unique symmetric Gaussian matrix as shown in the slide. So we find a solution of following linear system. Previous linear system can be modeled by means of conjugate gradient method. This method is an iterative method that involves three discrete Gaussian convolution as shown in the below of the slide. Now we introduce some preliminaries in order to make clear our main contribution. Let us consider S with 0 a general input signal, and the G is the Gaussian function with the standard deviation and the mean. The output of application of Gaussian, the output of Gaussian filter to the input S with 0 can be expressed by discrete Gaussian convolution. The output is the convolution of the input. Discrete Gaussian convolution are approximated by using Gaussian recursive filter. More precisely, we consider only the first order Gaussian recursive filter. Respectively, we see the first formula about the advanced filter and the second formula about the backing filter. The chosen coefficient, smoothing coefficient, guaranteed the convergence. So a detailed study has been done in the reference at below of the slide. Now we discretize the signal by using a grid. After we require to set this value for priming, advances, and backing filter respectively, or we can introduce the boundary condition in order to simulate the neglected equation. A study on boundary condition is confirmed in the reference below at the slide. More precisely, for priming, advancing, and backing filter, it is necessary to set this value for simulate the effect of neglected equation. We set this value by using the boundary condition. Therefore, starting from previous procedure, we can write this algorithm where in the first part the previous values has been set. After we start at line 8 and the line 12, the advances and backing filter. Now we see the second section about the parallel approach. We introduce the environment about our implementation has been developed by exploiting the powerful of most recent graphic process unit card, GPUs, and the CUDA framework has been used for developing the parallel implementation. So the reliable, and in order to make a reliable and performing parallel computation, our main implementation has been divided in three macro steps. The first step about domain decomposition, the second step about the local Gaussian convolution performed by each thread, and the third step about the total recollecting of local result to global output signal. We start to see the domain decomposition approach, in other words, in order to perform a fair workload distribution, a specific domain decomposition approach with overlapping has been employed. Indeed, we see the first partitioning of the original input signal as with 0 into T local blocks, where T is the number of threads. After we see some assumption where N is the problem size, and the D and R are variable used for distribution of local of starting input global signal to each thread. After each thread, add several entries of on the left and right boundaries in order to perform overlapping values to avoid the neglected equation boundary condition problem. And avoid the error introduced by perturbation error. A study confirmed this domain decomposition gain of performance obtained by this strategy in a study cited mentioned at below of the slide. We introduced the main GPU parallel algorithm related to implementation. We see in the first step about domain decomposition, where we set the local ID for each thread, and we distributed to each thread the local piece. After, in the second step, we performed the Gaussian convolution local about for each thread. At the end, the last step, the third step, is related to recollect local results to global output signal. We see more precisely, we see in detail each step about it. The first step computes the preliminary phase about the domain decomposition in order to make a good workload. More precisely, we define local stack for each thread in order to avoid any memory contention. Overlapping pieces are highlighted in small ping in the figures on the left. Artificial zero will be added if values on both sides do not exist. After the distribution, each thread starts its work on a one piece. After, the second step deals with the computation phase of Gaussian recursive filter locally. More precisely, each thread computes the forward and backward operation on each block, on each chunk distributed and divided, and starting first step. When possible, a dynamic parallelism is used. More in details, corresponding to iteration number k, a pool of k threads, start and execute the filter application when is possible, due to hardware resource limit. The last step, the third step, is related to is gathering the local result, all local results in an output signal vector. Each thread copies local result to global output by using the nlock variable related to size of only nlock value to copy from each thread to output vector, excluding the boundary elements of a local signal. According to with the upper bound theorem, related to avoid any memory contention by copying only nlock element from local thread to global memory. We see the last section about experimental result. We introduced the computer machine where we have developed and executed the test, the experimental test. We see this specification and introduce a brief memory approach about the suitable memory strategy in order to obtain a gain of performance about the increasing of the stack and the local heap for each thread, because the step is an hardware piece on GPU, and introduce a dynamic variation of fetch granularity L2 cache. Due to the nature of L2 cache, that is related to fetch each most used data from this memory. We introduced the first test about the execution time by varying iteration number and problem size by fix the block per threads grid has been fixed, 10 for 100, and m about the overlapping value is equal to 5. We can see how the GPU version on each row of this table is much faster than GPU version. Now we fix the the iteration number k equal to 500 in order to introduce the second test. Fixed the k equal to 500 iteration number, we introduce the second test by varying the CUDA configuration and the input size. Now we highlight how the gain of performance in time terms has been obtained about on each row of the table, and the best performance is about 3,000 threads. Now we fix this number of threads in order to introduce the third test about the fixed grid of threads, of CUDA threads, and we now are varying the problem size and iteration number. Now we can emphasize how the gain of performance significant good gain of performance has been obtained by using a full number of threads of our GPUs. The last test confirm our main contribution about the dynamic parallelism advantages. The dynamic parallelism has been used only by using a low number of threads due to hardware resource limit, because by applying and introducing a large number of threads, the other threads not works and the computation fails. Now we can highlight how the dynamic parallelism on the right is more performing by than of a single CUDA configuration without dynamic parallelism. Now we see the conclusion. In this work, a GPU parallel algorithm has been proposed about the Gaussian convolution, which is a fundamental step both in data assimilation and machine learning processes. It exploits a dynamic parallelism approach available on CUDA in specific context, both reliability and efficiency, and more precisely the gain of performance has been shown by experimental results. Thank you for attention. In this slide, you can see some contacts in order to have, if you have some question, to send us. Thank you for attention.
Hello, I'm Anko Adoan. I'm a postdoctoral researcher at the Technical University of Munich, and in this presentation I will be discussing how we can combine our physical knowledge of a given system and a machine learning framework called the ecostate network to reconstruct hidden state in a chaotic system. This work was done in collaboration with Dr. Luca Magri from the University of Cambridge and Professor Wolfgang Polifke from the Technical University of Munich. So what do I mean by hidden state? In many experiments, scientific experiments, we only have a limited amount of data. What do I mean by limited amount of data? I mean that sometimes we cannot measure some physical quantities because we don't have the apparatus necessary, or maybe because the quantity by itself cannot be measured. In some other circumstances, we can only have measurements in some parts of our experiments, and in other parts we cannot access those regions, and so we cannot put in measurement tools there to obtain the required information. And even in those circumstances when we can actually measure quantities, all the measurement tools have limited resolution. So sometimes we might not have an accurate resolution to observe in details the quantities that we want. And so that means that in all scientific experiments, there are some unmeasured or hidden states. And those states might actually be extremely important in describing the overall dynamics of the system. So this has been a large issue in any scientific experiments. In parallel, in recent developments in machine learning, all those recent algorithms in machine learning have shown capable of inferring relations between different quantities. And more than that, inferring and being able to some extent to reconstruct unmeasured or hidden states from available or measurable states. However, a big bottleneck or limitation of those machine learning tools is that when they are being trained, the machine learning algorithm needs a data set that contains both these hidden and measurable states. And obviously that's a roadblock, because creating these data sets of that contains hidden states is extremely difficult, because by definition those states are difficult to measure. And so in the rest of the presentation I'll show how we can use our physical knowledge to compensate for the fact that we cannot measure those hidden states and generate those data sets that contains these hidden states. And so more specifically, we will consider a dynamical system governed by this equation here, which is representative of any PDE. And so the full states here can be decomposed into a measured states. So the Z states are the ones that can be measured, and the H states are the ones that actually cannot be measured, so called the hidden states. And so the objective for us is to use a hybrid or physical knowledge, so the knowledge of the physical equations of the system, and a machine learning framework to reconstruct the hidden state H from the measurements of the measured state Z. And so to do that, we will be using a machine learning framework called the ecosystem network, which I will present next. I will show how to reconstruct hidden states in a prototypical chaotic system called the Lorenz system, and then I will summarize all the results shown in this presentation. So what is an ecosystem network? The ecosystem network is an extension of recurrent neural networks based on reservoir computing. So it is made so that it can approximate any dynamical system. It has been shown to be an universal approximator, meaning that there exists an ecosystem network that can approximate any dynamical system. And so the key aspect of the ecosystem network is the existence of this reservoir here, which is composed of a large number of neurons. And so the role of the reservoir is that it's a high-dimensional random system which is excited by the input. So it is connected to the input U, and the different neurons in the reservoir are being excited by it and then propagates this information from the excitation. And so the reservoir can be seen as a base for a nonlinear expansion of the system. So basically the reservoir is excited by the input U, and then it evolves in time, and then from the evolution of the neurons in the reservoir in time, we actually select a combination of them to actually obtain the prediction that we want. And so the reservoir acts as this nonlinear expansion and also as a memory of the input, because it propagates from neurons to neurons the input at a given time. And so, well, the key strength of the ecosystem network is that the output layer here is a very simple linear combination of the reservoir states. So that makes the reservoir to some extent simple to train, because we can obtain it just by using a width regression, for example. More specifically, how do we design an ecosystem network? So first we have this input layer, which is just a sparse matrix which is randomly initialized given some distribution. So basically this will specify how important are the inputs with regards to exciting the different neurons in the reservoirs. And then in the reservoirs, we have a matrix that specifies how the different neurons are connected to each other, and that matrix has to verify some properties called the ecostate properties that ensures that the dynamics within the reservoir present some specific quality. And so the dynamics in the reservoir is governed by these equations here, as you can see. So the future states of a given given neurons follows from the past states of the neurons through the connectivity matrix in the reservoir, and is also excited by the inputs here via the input layer. So now that we have the evolution of the reservoir states or the reservoir neurons, we can then deduce, using these linear methods, the estimated measured states and the hidden states. So this is the overall ecosystem network. So it is excited by our input signal, which only contains our measured states, so the Z data here, and then it has to output at the same time a prediction of the measured states and a prediction of the hidden states or the unmeasured states. So it has to be able to reconstruct the hidden state just based here on a partial observation of the full state, so the U or the measured state set. And so this, to obtain this reconstruction, we have a without matrix, which is then composed of two different parts. A part which has to provide the approximation of reconstruction, of the measured state, but also a part that has to provide a reconstruction of the hidden state H. Now, to get this without different stages that have to be followed. So in the first stage, we can reconstruct fairly straightforwardly the part of the readout that is linked to the measured states, which is provided here, and it can be obtained using a simple Ridge regression, given that we have the data of the measured states. So we can compute this Ridge regression, and we can show that this actually minimizes the L2 error between the measured states and the reconstructed and the approximated state from the ecostate network. In the second part, for the part of the readout which is linked to the hidden state, we can only randomly initialize it. It cannot, as we don't have any information or any data of those hidden states. And so finally, in the third part, first stage, we are actually going to combine our physical knowledge and this data-driven method. And so to combine those, we can actually combine them in the loss function, which we can use to minimize the overall readout. So in this loss function, which is written here, the first part is the error measure on the data. So we have this L2 error between the prediction of the ecosystem network, so Z hat, and the data that we can measure, which are the Z states here. And so we have a second term, which is where we have our physical knowledge that takes a role, because now that we have the prediction from the ecosystem network, it has the prediction from the entire state, from the full states of the system. And so using our knowledge of the physical equation, we can compute the physical residual, because we know the physical equations that govern our system. And so this physical residual has to be minimized to ensure that all the prediction of the ecosystem network are physical. And so we can add this second physics-based loss while training or physics-informed ecosystem network. And so this will provide the information to actually provide an accurate reconstruction of the hidden state. So now we illustrate this on. So the Lorenz system is composed of these three ODEs here, and it's a prototypical chaotic system. So here you have the trajectory of the of two originally very close trajectories which diverge after some times, which is typical of all chaotic systems. So we generated a data set here which contains more or less 200 Lyapunov of time. 200 Lyapunov of time being the time that it takes for two initially very close trajectories to diverge by an exponential. We generated using typical numerical schemes, and we generate our ecosystem networks so that it has those hyperparameters, and we consider in our problem that the phi3 states is unmeasured. So for the training of the ecosystem network, we will only provide its information of the phi1 and phi2 measurements, but the phi3 will not be provided at all to the ecosystem network. So now can the ecosystem network reconstruct these phi3 states? And this is what we see here, and we have in full black line the phi3 state, the true phi3 states. And we see that when we use an ecosystem network with a small number of neurons, so 50 in gray here, we manage some level of reconstruction, but there are inaccuracies whenever the phi3 state shows very large minimums. However, when we increase the number of neurons of the ecosystem network to 600 neurons, we see that it becomes much more accurate, and most of those small peaks here are better captured by the physics-informed ecosystem network with 600 neurons. And this better accuracy with larger reservoir comes from the fact that we have a larger pool of neurons from which the physics-informed ecosystem network can approximate the unmeasured dynamics. So by having a larger number of neurons, obviously we increase the expressivity of the physics-informed ecosystem network, and so it can find a better combination that allows it to reconstruct more accurately the phi 3 states and enforcing the minimization of the physical residual, and thereby obtaining a more physical reconstruction of the phi 3 states. So now another issue, and yes, another point that I would like to emphasize is that all this reconstruction of the phi 3 state is obtained without any measurements of the hidden states. So this is entirely driven by the use of our physical knowledge in the loss function during the training of the ecosystem network, physics-informed ecosystem network. So now another issue that often occurs in scientific measurements and experiments is that most measurement tools are affected by noise. So there is always some level of noise in the data, and so given that we are addressing an issue that can exist in experimental in scientific experiments, we are going to consider whether the physics-informed ecosystem network can accurately reconstruct unmeasured states when the measured states are actually affected by noise. And so we consider the same training data set as earlier, but where we add noise with a signal to noise ratio of 20 or 40 decibels. And so first, we can look at the reconstruction of the physics-informed ecosystem network on the measured states. So in blue here, you have the noisy data which is being used to train the physics-informed ecosystem network. In black line, you would see the non-noisy data, so our ideal data which does not have any noise. And you can see that the prediction of the physics-informed ecosystem network, the dashed red line, follows extremely well the full black line, which is the original non-noisy data. So in a way, the physics-informed ecosystem network has actually created, removed noise, which using its physical knowledge. So it has acted as a denoiser based on physical knowledge. So this is on the state for which we have some data, albeit noisy data. On states for which we have no data, so phi 3 here, we see that again we actually obtain a very good reconstruction of the unmeasured states. In the case of a low noise, so a signal to noise ratio of 40 dB, and we see that yes, that we have to some level a loss of accuracy when we have larger noise level, but that overall there is still a fairly good agreement between the physics-informed ecosystem network trained with noise and the true original data. Now that was shown for, those results were shown for some specific time series, but we can show a statistical error based on the overall reconstruction for the entire data set available. And we can see that overall, when we increase the number of neurons, we increase the accuracy, so we reduce the error, and that this is also observed when we have noisy data. So overall, we can consider that the physics-informed ecosystem network is robust with respect to noise, in the sense that it can reconstruct original the measured states without noise, and then it can also reconstruct the unmeasured state, even if it's trained with a given level of noisy data. So now, just to summarize, the proposed physics-informed ecosystem network was shown to be able to accurately reconstruct a hidden state, and without any data of the hidden state at any point during the training, and it is also robust with respect to noise. So we have shown that by considering training data sets that actually contains different level of noise. And so in ongoing work, we are actually applying these tools to high dimensional data, for example, fluid mechanical system. So Well, thank you for having watched this video.
Hope you enjoyed the video and all the presentations. I really want to thank you, the International Conference on Computational Science, for hosting our workshop. In particular, I want to thank you, Gabor, which is the thematic track program chair. Gabor has been very helpful and supportive, so thank you very much, Gabor. I want to thank you, Diana, the event manager of the Data Science Institute. Thanks to Diana, we put together this video, so thank you very much, Diana. And I want to thank you, the program committee of the workshop, all the reviewers, all the speakers, and all the people involved in this event. And I want to leave you with a quote of Albert Einstein, which I feel is true in general for science and research, but in particular in the intersection of different fields, where imagination is really a key point. I'm really looking forward to seeing you next year in person for the 3rd edition of the workshop. And I really want to wish you a good time. Bye-bye.